Hello there, and welcome to Just About Earth, where curiosity gets comfortable, questions slow down a little, and science is allowed to wander without needing to arrive anywhere too quickly. Wherever you happen to be listening from tonight, whether the lights are low or the day is just beginning to fade, I'm glad you're here. This is a place for unhurried thinking, for ideas that don't demand answers right away, and for letting the world feel slightly larger and slightly quieter at the same time. Tonight we're going to sit with a question that sounds simple at first, but grows more curious the longer you hold it. What if Earth is alive in a way we don't understand? Not alive like a dog or a tree or even a bacterium. Not alive in a way that fits neatly into biology, textbooks or lab definitions. But alive in some other sense. A sense that doesn't rush to explain itself. A sense that might feel familiar and strange at the same time, like recognizing a face in a crowd without knowing where you've seen it before. Before we ease into that thought, let me ask you something gentle and personal. Where are you listening from right now? Are you somewhere familiar or somewhere temporary? Is it late where you are or early? Are there sounds around you, or is the world unusually quiet? Questions like these don't need answers spoken out loud. They're just a way of settling into the moment, of noticing that you exist in a place, on a planet, at a particular instant that will never repeat itself in quite the same way. If you find this space calming, or if these kinds of slow questions help your mind unwind at the end of a long day, you're always welcome to like the video or subscribe. It helps this little corner of calm reach others who might need a pause too. No pressure at all. Think of it as leaving the door slightly ajar for future evenings like this one. Now, let's begin without hurrying. Imagine, for a moment, the Earth as you're used to seeing it. A sphere of rock and water and air. A planet orbiting a star at just the right distance. A system of plates, climates, oceans, and ecosystems governed by physical laws. That version of Earth is real, of course. It's measurable, observable, and endlessly studied. We've mapped it, drilled into it, photographed it from space, and broken it down into charts and models that fit neatly into screens and pages. And yet, even with all that knowledge, there's something about the planet that resists feeling fully understood. The way forests seem to breathe together across continents. The way oceans move heat around the globe with patient consistency. The way the atmosphere adjusts, responds, and sometimes pushes back. These behaviours don't mean intention or awareness in the way humans experience them, but they do suggest coordination. Not planned coordination perhaps, but emergent coordination. Patterns that arise not because something decided they should, but because countless smaller interactions happen to align. This is where the idea begins to shift, quietly and without drama. When we ask whether Earth might be alive, we're not necessarily asking whether it thinks, feels, or wants. We're asking whether our definition of life might be narrower than reality allows. After all, life as we usually define it is based on certain criteria: metabolism, reproduction, growth, response to stimuli, homeostasis. These are useful categories, but they're human-made categories. They reflect what we've observed so far, not necessarily what's possible in all forms. Consider how limited our perspective is by scale. A single cell doesn't know it's part of a body. It responds to chemical signals, exchanges energy, and performs its function without awareness of the larger organism it contributes to. From the cell's point of view, the body isn't alive in any meaningful sense. It's just an environment, a context, a set of conditions that change and apply pressure. Now zoom out again. From our point of view, Earth often appears the same way: an environment, a background, a stage where life happens rather than something participating in the process itself. We talk about life on Earth, not life as Earth. We treat the planet as a container rather than a system with its own dynamics that might be more than the sum of their parts. This way of thinking didn't arise by accident. For a long time, science made progress by separating things, studying organisms apart from their surroundings, studying geology apart from biology, studying weather apart from oceans. These divisions were useful, even necessary. They allowed us to understand details with clarity. But sometimes, when the pieces are studied in isolation for too long, it becomes easy to forget that they were never truly separate to begin with. The Earth doesn't behave like a pile of unrelated systems stacked together. It behaves like a web. Tug on one thread and others respond. Remove a forest and rainfall patterns shift. Warm the oceans slightly and weather systems reorganize themselves. Increase carbon dioxide and plant growth responds, sometimes in unexpected ways. These are not conscious reactions, but they are reactions nonetheless. They show sensitivity. They show feedback. Feedback is one of those words that sounds technical, but describes something very familiar. It's what happens when a system responds to its own changes. Your body does this constantly. When you get too warm, you sweat. When blood sugar rises, insulin is released. When something drifts out of balance, processes kick in to nudge it back. Not perfectly, not always successfully, but often enough to maintain a workable range. Earth does this too. Temperature changes trigger cloud formation. Ice reflects sunlight, cooling the planet, while darker surfaces absorb heat. Plants draw carbon from the air and release oxygen, altering atmospheric chemistry over long timescales. Oceans absorb heat and carbon, buffering rapid changes even as they slowly adjust. None of this requires intention, but it does require interaction. Continuous layered interaction across vast distances and times. At this point, it might be tempting to jump to a conclusion. To say yes, that means Earth is alive, or no, that's just complex chemistry and physics. But tonight isn't about settling the argument. It's about sitting with the question long enough for it to become interesting. Long enough to notice where our assumptions come from and how easily they guide our answers before we realise they're there. The word alive carries emotional weight. It suggests care, responsibility, relationship. If Earth were alive, even in an unfamiliar way, then our actions might feel less like resource management and more like interaction. That idea can be uncomfortable. It can also be clarifying. But before it becomes either, it helps to understand how deeply rooted the opposite idea is. The idea that Earth is inert, passive, a thing acted upon rather than an actor in its own right. That view fits neatly with industrial thinking. If the planet is just matter, then extraction is neutral. If it's just a backdrop, then damage is merely a technical problem to be solved later. Framing Earth as non-living has practical advantages. It allows us to use without listening, to change without asking, to treat consequences as external rather than internal. And yet, even as this view dominates modern life, traces of older perspectives linger. Many ancient cultures spoke of Earth as a mother, a being, or a presence. Not metaphorically, but relationally. Mountains were not just rock. Rivers were not just water. These weren't poetic flourishes. They were ways of understanding dependence and reciprocity in a world where survival required attention to cycles and limits. Modern science often distances itself from those ideas, and for good reason. Personification can blur accuracy. Metaphor can replace mechanism. But rejecting old language doesn't mean rejecting the observations behind it. Those cultures noticed patterns. They noticed balance and disruption. They noticed that when the land was overused, it responded, sometimes harshly. They lacked equations, but they weren't lacking awareness. As scientific tools improved, the language changed, but the underlying observations didn't disappear. They were reframed. Feedback loops replaced spirits. Systems replaced deities. Regulation replaced intention. In some ways, this made the planet seem less alive. In others, it made it more impressive. A world capable of regulating itself through countless interactions without a central controller is not simple. It's deeply complex. This complexity is what makes the question linger. What does it really mean to be alive? Is life defined by boundaries or by processes? Is it about individual units or about continuity? A beehive, for example, challenges simple definitions. No single bee contains the intelligence of the hive, yet the hive behaves in coordinated ways. Ant colonies farm, build, defend and adapt. We call the ants alive, but the colony itself operates almost like an organism. Earth, in comparison, is vastly larger and slower. Its signals move at geological speeds. Its responses unfold over decades, centuries, millennia. That makes them hard to notice in human lifetimes. But slowness doesn't equal absence. It just requires patience to perceive. There's also the issue of communication. We often associate life with communication that resembles ours. Signals, messages, responses we can recognize. Earth doesn't speak in words or gestures. It speaks in temperature gradients, chemical balances, population shifts, erosion patterns. If you're not listening in those languages, it's easy to assume nothing is being said. Imagine trying to explain human behavior to a creature that only lives for a few seconds. Our actions would appear static, random, unresponsive. The timescale mismatch would erase meaning. In a similar way, our relationship to Earth is shaped by the fact that we experience time very differently than the planet does. What feels like a sudden disaster to us might be a minor adjustment from a planetary perspective. What feels like stability might be a temporary pause in a much longer process. This doesn't mean Earth is indifferent. It means indifference might not be the right word. The planet doesn't prioritize human comfort, but it does maintain conditions that allow life, broadly speaking, to persist. And it has done so through dramatic changes. Ice ages, mass extinctions, volcanic winters, shifts that reset the board without erasing the game entirely. Life doesn't disappear when conditions change. It reorganizes. Different species rise, others vanish. Ecosystems reassemble themselves using whatever pieces remain. From a certain angle, this looks less like fragility and more like resilience. Not the resilience of individual creatures, but of life as a planetary phenomenon. Which brings us back gently to the central idea. If life is something that emerges from interaction, adaptation and continuity, then Earth doesn't sit outside of it. It participates, it shapes and is shaped. It provides conditions, but those conditions are actively maintained through ongoing processes rather than static design. This isn't a mystical claim. It's an observation about systems, about feedback, thresholds and regulation, about how the planet has remained within a relatively narrow temperature range for billions of years despite changes in solar output, about how atmospheric composition has shifted alongside biological activity in ways that keep certain balances intact most of the time. At this stage, nothing needs to be decided. No labels need to be applied. It's enough to let the idea breathe a little, to notice that the question itself opens doors rather than closing them. That thinking of Earth as possibly alive doesn't require abandoning science, but it might require widening the frame we use to interpret it. You're sitting on a planet that moves, adjusts, responds, and persists. A planet that has been doing so long before humans appeared and will continue long after we're gone. Whether or not we ever call that alive, it's worth paying attention to how deeply involved we already are in its ongoing story. There's a subtle shift that happens when you spend enough time thinking about Earth, and it doesn't arrive all at once. It doesn't announce itself. It doesn't come with a dramatic realization or a single fact that changes everything. Instead, it's more like the feeling you get when an object you've looked at your whole life suddenly stops behaving like an object at all. It begins to feel less static, less passive, less like something that simply sits there waiting to be described. For most of us, Earth begins as a thing, a globe in a classroom, a map on a wall, a background to human stories rather than a participant in them. We learn its dimensions, its layers, its orbit, its mass. We memorize names of oceans and continents. We colour in borders that don't exist outside our own agreements. All of this is useful, even necessary. But it also trains the mind to see the planet as finished, complete, defined. An object, after all, doesn't surprise you. It doesn't change unless acted upon. A chair remains a chair. A rock remains a rock. If something happens to them, it's because an external force intervened. This way of thinking slips easily onto the Earth itself. Volcanoes erupt because pressure builds. Storms form because conditions align. Continents drift because plates move. Each explanation is accurate, but taken together, they can give the impression that the planet is simply reacting, never participating. That impression starts to soften once you stop looking at individual events and begin noticing patterns over time. Not human time, which rushes forward in decades and lifetimes, but planetary time, which stretches so far that cause and effect blur into long conversations rather than sharp exchanges. When you step back far enough, Earth stops looking like a stage and starts looking more like a process. Take temperature, for example. Earth is not supposed to be as stable as it is. From a purely physical standpoint, the sun has grown brighter over billions of years. Early Earth should have been frozen solid. Later Earth should have overheated, and yet, for much of its history, liquid water has persisted. Not perfectly, not without interruption, but often enough to allow life to continue. That persistence is not guaranteed by physics alone. It emerges from interactions between atmosphere, oceans, rocks, and living organisms. Carbon dioxide dissolves in rain, weathering rocks. That weathering pulls carbon from the air and locks it into minerals. Over time, volcanic activity releases carbon back into the atmosphere. Plants draw it down again. Oceans absorb and release it based on temperature and chemistry. None of these processes know about each other, yet together they form a rough regulatory system. When things drift too far in one direction, other processes slowly respond. This is not intention, it's not awareness, but it is coordination, and coordination at that scale is hard to dismiss as mere coincidence. When enough of these feedbacks overlap, the planet begins to feel less like an object being pushed around, and more like something that maintains itself within limits. Another place this shift becomes noticeable is when you think about boundaries. Objects have clear edges. You can point to where they end and something else begins. Earth resists that simplicity. Where does the planet stop? At the surface, at the edge of the atmosphere, the furthest reach of its magnetic field. Each answer is technically correct, yet none of them feel complete. The atmosphere, for instance, is not a shell. It's a gradient. It thins gradually, mixing with space in a way that makes the boundary fuzzy rather than firm. That atmosphere isn't just sitting there either. It's constantly moving, redistributing heat, moisture, and energy around the globe. It connects distant regions in ways that make isolation impossible. A change in one place echoes elsewhere, sometimes half a world away. Objects don't behave like that. They don't have invisible extensions that influence distant systems. They don't depend on constant motion to remain what they are. Earth does. Then there's the issue of repair. Objects don't heal. If you crack a bowl, it stays cracked unless something external intervenes. Earth, on the other hand, is always reshaping itself. Erosion wears mountains down. Sediment fills basins. Tectonic plates recycle crust back into the mantle. Forests regrow after fires. Coral reefs rebuild after damage given time and conditions. This doesn't mean damage is harmless. Some changes are irreversible on human timescales. But the presence of repair mechanisms, especially ones that operate without direction or planning, adds to the sense that Earth behaves less like a broken thing and more like a system that adapts. The feeling deepens when you consider how life and the planet are inseparable. Life did not arrive on Earth and simply settle in. It transformed the planet. The oxygen in the atmosphere exists because early life released it as a waste product. That oxygen reshaped chemistry, geology, and climate. It rusted rocks. It cooled the planet. It made complex life possible, which then reshaped the planet further. In return, the planet shaped life. Gravity determined body plans. Climate shaped migration and metabolism. Oceans influenced chemistry and evolution. This back and forth has been happening for so long that separating life from Earth becomes increasingly artificial. They are not two things interacting. They are one process expressed in different forms. Once you see this, the language of objecthood begins to feel inadequate. Objects don't co-evolve with their contents. Objects don't rewrite their own conditions through internal activity. Earth does. Another clue lies in how sensitive the planet is to disruption. Sensitivity is often associated with living systems. A rock doesn't care if you remove a piece of it. A living system responds. Earth responds too, though not always in ways we expect or desire. Remove forests and rainfall patterns change. Heat the atmosphere and ice retreats. Sea levels rise and circulation shifts. These responses are not arbitrary. They follow pathways shaped by existing connections. Sensitivity does not imply fragility alone. It implies responsiveness. A thermostat responds to temperature changes. A body responds to infection. Earth responds to energy imbalances and chemical shifts. The response may be slow, it may overshoot, it may create new problems, but it is a response nonetheless. This is often where discomfort enters the conversation. Calling Earth responsive can sound like assigning intention where none exists. But responsiveness does not require awareness. A reflex does not require thought. A feedback loop does not require desire. Systems can respond without knowing they are doing so. The discomfort perhaps comes from what follows. If Earth is responsive, then our actions are not simply external forces acting on an inert object. They become inputs into a system that will answer back in its own way, on its own timescale. That answer may not align with human priorities. At this point, the idea of Earth as an object begins to feel less stable. Objects don't push back. They don't alter their behaviour based on accumulated changes. They don't have histories that shape future responses. Earth does. History matters here. Not just human history, but planetary memory. Past climates leave traces in ice cores, sediments, and rocks. Those traces influence future processes. The arrangement of continents affects ocean currents. Past extinctions shape present ecosystems. The planet carries its past forward, not as recollection, but as structure. This kind of memory is another feature that complicates the object metaphor. Objects don't remember, systems do. Memory doesn't require a brain, it requires persistence of change. Earth has that in abundance. It's also worth noticing how often we already slip into different language without realizing it. We talk about the planet being out of balance, about systems being stressed, about tipping points and thresholds. These are not terms usually applied to objects. They belong to dynamic systems that can change states based on internal conditions. A bridge can collapse, but it doesn't experience strain in the same way a body does. Earth, when pushed beyond certain limits, reorganizes. Ice sheets collapse. Circulation patterns shift. Ecosystems transform. These changes are not random. They follow from the internal structure of the system. At some point, the question stops being whether Earth is alive and becomes whether the distinction we're making is useful. If the object model fails to capture essential behavior, perhaps it's the model that needs adjusting. This doesn't mean abandoning precision or rigor. It means choosing metaphors that align with observed behavior rather than forcing behavior to fit familiar metaphors. Science evolves not just through new data, but through better frames for interpreting that data. There's also a psychological aspect to this shift. Seeing Earth as an object places humans at the centre. The planet becomes something we use, manage, and optimize. Seeing Earth as a system, we're embedded in changes that orientation. It doesn't remove human importance, but it situates it differently. In a system, actions have consequences that circle back. Outputs become inputs. Control becomes partial rather than total. Responsibility becomes shared rather than externalized. This can feel unsettling, especially in cultures built on mastery and control. But it can also be grounding. It reminds us that we're not separate from the conditions that sustain us. As this perspective settles in, the planet starts to feel less like a possession and more like a presence. Not a presence with intentions or feelings, but a presence in the sense of something that exists alongside us, interacting continuously. Something that shapes the space of possibility we inhabit. This doesn't demand reverence or fear, it demands attention. Attention to connections that are easy to ignore when everything is reduced to objects and resources. Attention to timescales that don't match our own. Attention to signals that aren't designed for human senses. None of this resolves the original question. It doesn't need to. The value lies in allowing the question to loosen rigid categories, to make space for the idea that Earth might not fit neatly into the boxes we inherited, that it might be doing something more complex than being acted upon. For now, it's enough to notice the shift, the quiet moment when the planet stops feeling like a thing and starts feeling like a system you're inside of, a system that moves slowly, responds indirectly, and carries its past forward into every present moment. Staying with that feeling doesn't require belief or agreement, it only requires patience. Long before satellites traced cloud bands across the globe, and long before diagrams reduced the planet to layers of crust, mantle and core, there was a quieter assumption shared by many early cultures. The Earth was not merely a lump of matter drifting through space. It was not just ground underfoot or scenery behind human affairs. It was something with presence, history and consequence. Not alive in a biological sense, at least not as we would define it today, but certainly not inert, certainly not meaningless. This idea did not emerge from superstition alone, nor was it born from ignorance of physical processes. It came from lived experience. When survival depended on rainfall, soil fertility, seasonal rhythms, and the stability of land and water, the planet did not feel like an object. It felt like a participant, something that responded, sometimes generously, sometimes harshly, to how it was treated. In many early societies, the Earth was not named as a thing, but addressed as a being. Not always kindly, not always predictably, but always with the understanding that actions had consequences beyond immediate cause and effect. Overuse land and crops fail. Ignore seasonal signals and famine follows. Pollute water and sickness spreads. These were not abstract lessons. They were patterns observed across generations, remembered not in data tables but in stories, rituals, and taboos. Calling the Earth a mother, a spirit, or a living presence was not necessarily a claim about anatomy or consciousness. It was a way of encoding relationships, a way of reminding communities that the ground beneath them was not passive, that it could be damaged, that it could recover, that it set limits even when those limits were inconvenient. As scientific thinking developed, especially in the modern Western tradition, much of this language was set aside. Personification was seen as misleading. Agency was reserved for organisms with nervous systems. The Earth became a planet, a rock, a sphere governed by laws that could be measured and predicted. In many ways, this shift was necessary. It allowed for extraordinary advances in understanding. But something subtle was lost along the way. When Earth was reframed as just a rock, the emphasis shifted from relationship to control. Rocks do not negotiate. Rocks do not respond meaningfully. Rocks can be broken apart and rearranged without expectation of retaliation or long-term consequence. This framing fit neatly with emerging industrial societies that required resources at scale. Forests became timber, rivers became infrastructure, land became property. And yet, even as this view took hold, it never fully erased older intuitions. They lingered at the edges of culture, often dismissed as symbolic or emotional, but still present. Farmers still spoke of land being tired. Sailors still treated the sea with a respect that bordered on cautionary reverence. Indigenous knowledge systems, many of which were sidelined or suppressed, continued to describe Earth as dynamic and relational rather than inert. What's interesting is that as scientific understanding deepened, it began, slowly and unintentionally, to circle back towards some of these earlier ideas. not in language at first, but in observation. Scientists studying climate notice self-regulating processes. Biologists studying ecosystems notice stability emerging from interaction rather than design. Geologists studying Earth's history noticed long-term patterns that looked less like random accumulation and more like sustained balance punctuated by disruption. None of this required spirits or intentions, but it did challenge the idea that Earth was simply a backdrop. It suggested instead that the planet had properties that only made sense when viewed as a whole, properties that disappeared when broken down into isolated components. One of the earliest scientific figures to wrestle with this tension was Alexander von Humboldt. Writing in the late 18th and early 19th centuries, Humboldt described nature as an interconnected web. He observed how climate, vegetation, altitude, and geography influenced one another. He resisted reducing nature to separate parts. Instead, he emphasized relationships. His work influenced generations of scientists, even as the dominant trend moved towards specialization and fragmentation. This tension between holistic and reductionist views has never fully resolved. It surfaces repeatedly whenever scientists encounter systems that behave in ways too complex to predict from individual parts alone. Earth is perhaps the largest such system we study directly, and it has a habit of defying simple categorization. Long before modern science, philosophers also struggled with Earth's status. In ancient Greece, thinkers like Plato and Aristotle debated whether the cosmos was alive. Plato in particular described the world as a single living creature endowed with a soul, not in a religious sense, but as a way of expressing order and coherence. Aristotle, more grounded in observation, still saw nature as purposeful, though not conscious in the human sense. These ideas were not universally accepted, nor were they precise by modern standards, but they reflect a persistent discomfort with treating the world as dead matter alone. That discomfort resurfaced again and again, even as scientific frameworks became more formal. During the Enlightenment, mechanistic views dominated. The universe was likened to a clock, predictable, law-bound, impartial. Earth, in this model, was part of the machinery. A complex machine perhaps, but still a machine. This metaphor proved enormously productive. It allowed scientists to calculate orbits, predict tides, and understand physical forces with unprecedented accuracy. However, machines are built. They do not grow. They do not evolve internally. Earth does both. Its continents shift. Its atmosphere changes composition. Its oceans circulate differently over time. These are not adjustments made by an external designer. They arise from internal dynamics. As geology matured as a science, it revealed a planet far older and more active than previously imagined. Mountains were not static monuments. They rose and eroded. Seas advanced and retreated. Entire environments vanished and reappeared elsewhere. Earth was not finished. It was ongoing. This realization unsettled the idea of a static object-like planet. Objects do not have deep histories that actively shape their present behavior. Earth does. Its past is not buried and irrelevant. It is folded into current processes, influencing everything from soil composition to atmospheric circulation. Biology added another layer to this discomfort. Once it became clear that life had radically altered the planet, the boundary between Earth and its inhabitants blurred further. Oxygen, once toxic to early life, accumulated because life produced it. That accumulation transformed the planet's chemistry, climate, and geology. Rocks oxidized, new minerals formed, entire metabolic pathways evolved in response. This was not life adapting to Earth alone, it was Earth adapting to life. The two changed together. Over billions of years, this mutual influence became so deep that separating cause from effect became nearly impossible. This coevolution echoes older intuitions that Earth was never just a stage. It was involved, active. changed by what lived upon it and changing those lives in return. Even the word environment subtly reinforces objecthood. It implies surroundings rather than participation. But when you look closely, Earth is not around life. Life is threaded through Earth. Microbes live in rocks, bacteria shape clouds, plants influence rainfall, animals redistribute nutrients across landscapes, humans alter atmospheric chemistry at a global scale. At this point, calling Earth just a rock begins to feel less like a scientific conclusion and more like a convenient simplification. Useful in certain contexts but incomplete. It strips away interaction in favour of material description. It privileges components over relationships. Interestingly, many cultures that retained relational views of Earth did not see this as sentimental. It was pragmatic. Treating Earth as responsive encouraged caution. It discouraged overreach. It embedded long-term thinking into daily decisions. When land is seen as alive or sacred, exploitation carries moral weight. Modern societies often struggle to recreate this restraint through regulation and policy, attempting to manage an inert world that keeps behaving dynamically. Climate change is a clear example. The assumption that the atmosphere could absorb endless emissions without significant response proved incorrect. The system answered back, slowly at first, then with increasing clarity. This does not mean earlier cultures were infallible or scientifically accurate in all respects, but it does suggest that dismissing their perspectives entirely may have cost us something important. They noticed limits, they respected thresholds, they understood dependence intuitively. In recent decades, scientists have begun to revisit these older ideas with new tools, not by reintroducing myth, but by recognizing that complexity and emergence require different conceptual frames. Systems theory, Earth system science, and ecology all emphasize interaction over isolation. These fields do not claim Earth is conscious. They do not claim it has intentions. But they do describe a planet that maintains conditions, responds to disturbance, and evolves as a whole. A planet that cannot be fully understood by examining pieces alone. At some point, the language of objecthood simply runs out of usefulness. It cannot easily describe self-regulation without invoking contradiction. It cannot account for planetary scale feedbacks without borrowing terms usually reserved for living systems: balance, stress, resilience, recovery. The discomfort with these terms often reveals more about our assumptions than about the planet itself. We are accustomed to reserving certain words for ourselves. When those words begin to apply elsewhere, even metaphorically, it challenges our sense of uniqueness. But perhaps the older idea was never about diminishing humanity. Perhaps it was about situating humanity, about recognizing that being part of a larger system does not make us insignificant. It makes us responsible. This idea does not require belief in an Earth spirit or planetary consciousness. It requires acknowledgement that the planet is not neutral ground, that it participates in shaping outcomes, that it responds to cumulative actions in ways that are not always predictable or reversible. As this perspective settles, the old stories begin to look less like naive personification and more like early attempts to describe complexity without equations. They used narrative because narrative was available. We use models because models are available. Both are responses to the same challenge: how to make sense of a world that is more than the sum of its parts. Moving forward, the question becomes less about whether the Earth is alive and more about how we describe what it does. What language captures responsiveness without implying intention? What metaphors illuminate without misleading? What frames encourage humility rather than dominance? The old idea that Earth was never just a rock persists, because the rock metaphor fails under pressure. It collapses when faced with feedback, memory, and co-evolution. Something else is needed. Something that acknowledges material reality without denying relational dynamics. It's enough to recognize that the idea is not new. It's been with us for as long as humans have tried to understand their place in the world. It fades, returns, reshapes itself, and persists because the planet itself keeps behaving in ways that resist being reduced to stone alone. At first, coincidence is the most comfortable explanation. It asks very little of us. When two things happen together, we can shrug and move on. When patterns appear, we can dismiss them as chance alignments, temporary overlaps, or statistical noise. Coincidence keeps the world simple. It preserves the idea that events are isolated unless proven otherwise. For a long time, this way of thinking shaped how humans understood the Earth. Rain followed seasons, rivers flooded, forests grew and burned, ice advanced and retreated. These events were observed, recorded, and often explained locally. A flood happened because of heavy rain. A drought happened because rain failed to arrive. A volcanic eruption happened because pressure built underground. Each explanation was accurate in its own narrow frame. But accuracy at small scales can sometimes hide larger connections. The shift away from coincidence did not begin with a single discovery. It emerged slowly as observations accumulated and refused to stay isolated. Scientists began noticing that certain changes did not occur randomly. They clustered, they repeated, they followed rhythms that extended far beyond any single cause. One of the earliest clues came from climate records hidden in unexpected places. Ice cores drilled from Greenland and Antarctica revealed layers upon layers of frozen history. Each layer held tiny bubbles of ancient air, preserved snapshots of atmospheric composition, stretching back hundreds of thousands of years. When scientists analysed these layers, they saw clear patterns. Carbon dioxide levels rose and fell in step with temperature. Temperature changes aligned with shifts in ocean circulation. Volcanic eruptions left chemical signatures that echoed across the globe. At first glance, these might still be treated as coincidences. After all, many things change over time. But the regularity was difficult to ignore. When one variable shifted, others followed in predictable ways. This was not randomness, it was relationship. The same realization unfolded in the study of ecosystems. Early ecologists often focused on individual species. Predators ate prey, plants competed for light, animals migrated based on food availability. But as long-term data accumulated, it became clear that ecosystems behaved more like networks than collections. Remove a single species, and the effects rippled outward. Predator loss led to prey overpopulation. Overgrazing altered plant communities. Soil erosion increased. Water cycles shifted. These cascading effects were not accidents. They followed pathways shaped by existing connections. Once scientists began mapping these connections, coincidence gave way to structure. What looked like unrelated outcomes were often different expressions of the same underlying change. One particularly striking example comes from the oceans. For centuries, sailors noted that certain regions were more productive than others. Fish appeared in abundance in some places and vanished from others without obvious cause. It was tempting to attribute this to luck or mystery, but oceanographers eventually uncovered patterns of upwelling, where deep, nutrient-rich waters rise to the surface due to wind and current interactions. These upwellings fueled plankton growth, which supported fish, birds, and mammals. Suddenly, abundance was no longer coincidental. It was tied to invisible processes moving heat, nutrients, and energy across vast distances. Changes in wind patterns thousands of kilometers away could alter entire marine ecosystems. The planet was connecting dots we hadn't known were related. Atmospheric science followed a similar path. Weather was once treated as inherently chaotic beyond short timescales. While day-to-day variability remains difficult to predict, larger patterns began to emerge with better data. Jet streams influenced storm tracks. Ocean temperatures affected rainfall on distant continents. El Niño and La Niña events linked Pacific Ocean conditions to weather across the globe. Again, coincidence lost ground. Floods in one region aligned with droughts in another. Heat waves appeared alongside shifts in ocean circulation. These were not isolated accidents. They were signatures of a system redistributing energy. As pattern recognition improved, scientists became more cautious about dismissing correlations. Correlation alone does not prove causation, but repeated correlations across time and space suggest structure, and structure implies organization, even if that organization arises without design. Geology added another layer to this evolving view. Plate tectonics, once controversial, revealed that continents were not fixed. Their movement explained the distribution of mountains, earthquakes, and fossils across oceans. Coal deposits appeared in polar regions. Tropical fossils emerged in temperate zones. These patterns only made sense once continents were understood as mobile participants in a dynamic system. With this realization, Earth's history began to look less like a random sequence of events and more like a narrative shaped by constraints and feedbacks. Ice ages aligned with orbital variations. Volcanic episodes coincided with mass extinctions. Recovery followed disruption in ways that repeated across deep time. The language scientists used began to change. Words like cycle, loop, and regulation entered discussions once dominated by linear cause and effect. These terms implied recurrence and connection rather than one-off events. One of the most important shifts occurred when scientists stopped asking what caused a single change and started asking how systems responded to change. This reframing altered the interpretation of data. Instead of seeing a rise in temperature as an isolated anomaly, researchers examined how ice, oceans, vegetation, and atmosphere reacted together. Instead of treating extinction events as purely destructive, they studied how ecosystems reorganized afterward. This systems perspective made coincidence increasingly implausible. When multiple components responded in coordinated ways, explanation required more than chance. It required acknowledging that Earth's parts were interacting continuously. The resistance to this idea was not purely scientific, it was conceptual. Recognizing patterns meant accepting that the planet behaved as an integrated whole. That challenged long-standing assumptions about separability. It also raised uncomfortable questions about predictability and control. Systems with feedbacks can behave non-linearly. Small changes can produce large effects. Stability can persist until it suddenly doesn't. This discomfort was evident in early reactions to climate modelling. When models suggested that human activity could alter global systems, critics often framed the results as coincidental correlations or exaggerated projections. It was easier to believe that changes were natural variability rather than responses to new inputs. Coincidence felt safer than responsibility. But as evidence accumulated, coincidence became harder to defend. Temperature trends aligned with greenhouse gas emissions. Ocean acidification tracked carbon absorption. Ice loss accelerated alongside warming. These relationships persisted across independent data sets and methodologies. They told the same story from different angles. At some point, refusing to see patterns required more explanation than accepting them. The burden of proof shifted. Systems thinking moved from speculative to necessary. What's important here is not that Earth behaves predictably in all respects. It doesn't. Complexity ensures variability, but complexity does not mean randomness. It means outcomes depend on interactions rather than single causes. Seeing patterns where coincidence once reigned requires patience. It requires long records, broad perspectives, and willingness to revise assumptions. It also requires humility. Patterns do not always announce themselves clearly. They emerge slowly, often contradicting expectations formed from smaller scales. There's also a human tendency to underestimate connectedness. Our brains evolved to track immediate cause and effect. We're good at noticing direct interactions. We're less adept at perceiving delayed, distributed responses. Earth operates heavily in that delayed and distributed space. Carbon released today influences climate decades from now. Deforestation alters rainfall patterns years later. Chemical pollutants circulate globally before settling. These lags obscure relationships, making coincidence seem plausible until the full arc is visible. Once patterns are recognised, they change how we interpret present events. A heat wave is no longer just weather. It's part of a broader energy imbalance. A coral bleaching event is not an isolated tragedy. It's linked to temperature, acidity, circulation, and stress thresholds. Each event becomes a data point in an ongoing process rather than a standalone occurrence. This shift in perception also influences how we think about stability. Stability no longer means unchanging. It means regulated. It means fluctuations within bounds maintained by feedbacks. When feedbacks weaken or reverse, stability can give way to rapid change. Earth's history is filled with such transitions. Long periods of relative balance interrupted by abrupt shifts. These shifts often followed the accumulation of pressures rather than single triggers. Coincidence cannot easily account for that structure. Patterns can. As this understanding deepens, the idea of Earth as an object continues to erode. Objects do not exhibit coordinated responses across scales. They do not reorganize themselves following disturbance. They do not carry internal dynamics that buffer change until thresholds are crossed. Earth does all of this, not because it is alive in a familiar sense, but because it is complex in a way that demands a different lens. Seeing patterns also reshapes how we view human influence. Humans are not external forces acting upon a passive planet. We are components introducing new variables into existing systems. Our actions alter feedbacks. They shift baselines. They accelerate processes that once unfolded slowly. This realization can feel overwhelming. Patterns imply predictability, but they also imply responsibility. If actions have system-wide consequences, then ignorance becomes less defensible. Coincidence offers escape. Patterns demand engagement. Importantly, seeing patterns does not mean seeing everything. Earth remains partially opaque. There are interactions we do not fully understand, feedbacks we cannot yet model accurately, thresholds we cannot precisely locate. Pattern recognition is an ongoing process, not a finished map. But even incomplete patterns are powerful. They allow us to anticipate directions, if not exact outcomes. They reveal vulnerabilities. They show where resilience exists and where it may fail. As scientific disciplines increasingly overlap, pattern recognition becomes unavoidable. Climate science intersects with ecology. Ecology intersects with geology. Geology intersects with chemistry. Each field contributes pieces that only make sense when assembled. This convergence mirrors the older intuitions discussed earlier. The sense that Earth is not a collection of separate things, but a woven whole. Modern science arrives at this view not through story or myth, but through data that refuses to stay compartmentalized. At some point, coincidence stops being an explanation and starts being a placeholder for incomplete understanding. Patterns take its place not because they are comforting, but because they are more accurate. The moment when scattered observations align, when repetition replaces randomness, when Earth's behavior begins to look less like a series of accidents and more like the expression of an underlying structure that has been there all along, waiting to be noticed. There is a habit in human language that quietly shapes how we understand the world. We describe breathing as something animals do, inhaling, exhaling, a rhythmic exchange that keeps bodies alive. Plants, by contrast, are often described as passive. They grow, they sit, they absorb sunlight. Even when we learn about photosynthesis, it's usually framed as a chemical process rather than a bodily one. Useful, yes. Vital, certainly. But not something that feels alive in the way breathing does. That perception begins to change when you stop thinking about individual trees and start thinking about forests as systems. Not collections of plants, but coordinated assemblies of living matter, exchanging gases with the atmosphere on a scale large enough to shape the planet itself. At that point, the metaphor of breathing becomes harder to dismiss. Not because forests have lungs, but because the exchange they participate in is rhythmic, responsive, and essential to planetary balance. Every leaf is a surface. Millions of microscopic pores called stomata open and close in response to light, moisture, temperature, and internal chemistry. Through these openings, carbon dioxide enters. Oxygen and water vapour leave. This happens constantly, across billions of leaves, across continents. The motion is invisible, silent. But the volume is enormous. Forests move gases in quantities that rival industrial activity, and they do so continuously, day after day, year after year. During daylight, forests draw carbon dioxide from the air. They use the energy of sunlight to rearrange its atoms, building sugars that become wood, roots, bark, and soil carbon. Oxygen is released as a byproduct. At night, respiration dominates. Oxygen is consumed. Carbon dioxide is released. The balance between these processes changes with season, weather, and forest health. Seen from this perspective, forests do not merely exist within the atmosphere. They actively participate in shaping it. The composition of the air above a forest is measurably different from the air above a city or an ocean. Multiply that difference across the world's forests, and you begin to see how vegetation acts as a planetary scale regulator. This is not metaphorical breathing. It is gas exchange driven by biological activity, and it is one of the primary reasons Earth's atmosphere remains suitable for complex life. What makes this exchange particularly striking is how responsive it is. Forests do not absorb carbon at a constant rate. They adjust. During droughts, stomata close to conserve water, reducing carbon uptake. During periods of ample moisture and warmth, uptake increases. After disturbances like fires or storms, uptake may decrease temporarily, then recover as regrowth begins. These adjustments are not coordinated by a central command. Each plant responds locally to conditions, yet collectively these local responses scale up into global patterns. Satellite measurements show seasonal breathing of the planet itself. Carbon dioxide levels in the atmosphere rise and fall each year, decreasing during growing seasons and increasing during dormant periods, especially in the northern hemisphere where land vegetation is extensive. This annual oscillation is one of the clearest signals of life's influence on Earth's atmosphere. It is a pulse, not a metaphorical one, but a measurable fluctuation tied directly to photosynthesis and respiration. The planet's air composition changes because forests grow, rest, and grow again. The quietness of this process makes it easy to overlook. There are no dramatic sounds, no visible motion from a distance. But silence does not mean inactivity. Much of Earth's most consequential work happens quietly. Tectonic plates creep. Oceans circulate. Forests exchange gases. These processes do not announce themselves, but they shape everything. Forests also influence climate in ways that go beyond carbon alone. Trees release volatile organic compounds, tiny molecules that contribute to cloud formation. These compounds can encourage the condensation of water vapour, increasing cloud cover and, in some cases, rainfall. Forests do not just respond to climate, they help create it. This feedback can be subtle or powerful depending on scale. In large tropical forests, such as the Amazon, moisture released through transpiration contributes significantly to regional rainfall. Air masses moving over the forest pick up water vapour, which later falls as rain, sometimes hundreds or thousands of kilometres away. Remove enough forest, and this cycle weakens. Rainfall patterns shift. Dry seasons lengthen. Here again, coincidence falls apart. Forest loss does not merely remove trees, it alters atmospheric behaviour. The forest was part of the system that generated its own supporting conditions. When that participation is reduced, the system responds. This responsiveness complicates the idea of Earth as a passive environment. The planet's atmosphere is not simply a container for gases, it is an active participant in a continuous exchange with living systems. Forests are not decorations on the surface. They are interfaces between land and air. The word interface is important here. Interfaces are zones of exchange. They are where systems meet and interact. Leaves are interfaces. Soil surfaces are interfaces. Forest canopies are massive, layered interfaces connecting ground, vegetation, atmosphere, and sunlight. Through these interfaces, energy and matter flow. When you begin to see forests this way, they stop feeling like static scenery. They begin to feel like organs within a larger system. Not organs with consciousness or intention, but organs in the sense of specialized structures performing essential functions that support the whole. This framing is not universally comfortable. Comparing forests to organs invites the idea of a planetary body, which edges toward language some scientists prefer to avoid. But discomfort does not negate usefulness. If a metaphor helps clarify function without misleading about mechanism, it has value. Forests also store memory. Carbon absorbed during photosynthesis becomes part of tree rings. Each ring records conditions during the year it formed. Wide rings signal favourable growth. Narrow rings indicate stress. Over centuries, forests archive climate history in wood. When trees die and fall, some of that carbon enters soils, where it can remain for decades or centuries more. Soils themselves are dynamic. Microbes decompose organic matter, releasing gases back into the atmosphere. Roots exude compounds that feed microbial communities. Fungi form vast underground networks, connecting trees and facilitating nutrient exchange. This underground activity further complicates the idea of forests as collections of individual plants. A forest is not just trees, it is roots, fungus, microbes, insects, animals, and soil, all participating in chemical exchanges that affect the air above. Remove any major component, and the behaviour of the whole changes. The atmosphere responds in turn. Rising carbon dioxide concentrations influence plant growth. In some cases, increased CO2 can stimulate photosynthesis, leading to faster growth. But this effect is limited by nutrients like nitrogen and phosphorus. Without those, extra carbon cannot be fully utilised. Growth responses vary by species and region. This uneven response introduces further complexity. Forests in some areas may temporarily absorb more carbon, while others struggle under heat stress or drought. The planetary breathing becomes irregular, shaped by local conditions amplified at scale. There is no guarantee of balance here. Feedbacks can stabilise or destabilise depending on context. A forest that absorbs carbon may slow warming locally, but warming may also increase fire frequency, releasing stored carbon back into the atmosphere. The direction of the response depends on thresholds and timing. This uncertainty is not a flaw in the concept. It is a feature of complex systems. Breathing organisms do not always breathe evenly. Illness alters respiration. Stress changes rhythm. Recovery takes time. Seeing forests as participants in atmospheric exchange encourages a shift in attention. Instead of asking only how much carbon they store, we begin asking how resilient their processes are. How do they respond to heat, to drought, to fragmentation, to pollution? These questions matter because they determine how the planetary exchange evolves. It also reframes deforestation. Cutting down trees is not merely removing biomass, it is interrupting an exchange. It is altering the interface between land and air. The effects propagate outward, influencing climate, water cycles, and atmospheric chemistry. This reframing does not require moral language. It does not require assigning rights or intentions. It requires recognizing function. Forests perform work. That work has consequences beyond the forest itself. The idea that forests breathe has appeared in many cultures long before scientific measurements confirmed gas exchange at scale. While earlier descriptions lacked chemical detail, they captured something important. The sense that forests were alive in a way that mattered to the air, the rain, and the health of the land. Modern science does not need to adopt the older language wholesale, but it benefits from acknowledging that the underlying intuition was not wrong. It was incomplete, but directionally accurate. What science adds is precision. We can measure fluxes, we can track seasonal cycles, we can quantify how much carbon moves through forest systems each year. We can observe how disturbances alter these flows. With that precision comes responsibility. Once patterns are measured, they cannot be unseen. The knowledge that forests regulate atmospheric composition changes how we interpret their loss. It becomes harder to frame deforestation as a local issue when its effects ripple globally. This does not mean forests are fragile in a simplistic sense. Many forests recover from disturbance. Succession replaces loss. New growth emerges, but recovery depends on conditions. Repeated stress can overwhelm regenerative capacity. Time matters. Time, again, introduces scale mismatch. Forest processes operate over decades and centuries. Human decision-making often operates over years or less. The exchange of gases continues regardless, but its character changes depending on what remains to participate. As this understanding settles, the image of Earth shifts again. The planet begins to feel less like a container and more like a system whose components actively shape shared conditions. Breathing in this sense is not centralized. It is distributed. It happens everywhere life meets air. This distributed breathing does not require coordination to function. It emerges from countless local interactions. That emergence is what gives it stability and vulnerability at the same time. Stable because no single tree controls the process. Vulnerable because cumulative losses add up. There is a temptation to romanticize this picture, to imagine forests gently tending the atmosphere with benevolent intent. That temptation should be resisted. Forests do not act for the planet's benefit. They act to survive. The fact that their survival supports broader balance is a consequence, not a goal. But consequences matter regardless of intention. The planet's atmosphere is shaped by outcomes, not motivations. Understanding this helps ground the idea of Earth as possibly alive in a non-sentimental way. Life, at scale, creates conditions that support more life. It does so through processes that look purposeful without being planned. Forest breathing is one such process. It is enough to linger with forests, with the quiet opening and closing of stomata, with the slow movement of carbon from air to wood to soil and back again, with the realization that the air you breathe tonight has likely passed through leaves countless times before reaching you. That circulation does not announce itself. It does not demand recognition. But once noticed, it becomes difficult to forget. The atmosphere feels less like empty space and more like shared breath. And the planet, through its forests, feels less like a rock and more like a system constantly exchanging with itself, maintaining conditions that make nights like this possible. If forests quietly exchange gases with the air, then oceans move energy and matter with a patience that is harder to notice, but no less consequential. From the surface, the sea can appear still or chaotic, depending on the weather. Waves rise and fall, storms churn the top layers. But beneath that surface activity lies something far more consistent. A slow, global movement that links distant regions, redistributes heat, carries nutrients, and stabilizes conditions over time. When viewed this way, oceans begin to feel less like vast containers of water and more like circulatory systems operating at a planetary scale. Circulation is not about speed, it is about continuity. Blood moves through the body not in dramatic surges but in steady flow, reaching extremities, returning inward, carrying oxygen, heat, and waste. Ocean circulation works in a similar way, though stretched across thousands of kilometers and unfolding over years, decades, and even centuries. Warm water travels, cold water sinks. Density differences drive motion. The result is a global pattern of movement that links poles to tropics and surface to depth. One of the most important drivers of this movement is temperature. Warm water is less dense than cold water, so it tends to remain near the surface. Cold water, heavier and denser, sinks. Salinity also matters. Saltier water is denser than fresher water. Where temperature and salinity combine in particular ways, water masses form that either rise, sink, or slide along layers of similar density. These differences create pressure gradients that keep water moving even in the absence of wind. This movement is not random. It follows pathways shaped by Earth's rotation, the arrangement of continents, and the geometry of ocean basins. Currents curve because of the Coriolis effect. They accelerate where coastlines funnel them. They slow where basins widen. Over time, these pathways become persistent features of the planet, as reliable as mountain ranges, though far less visible. One of the best-known examples is the Atlantic meridional overturning circulation. Warm surface water flows northward from the tropics, carrying heat toward Europe. As it cools and becomes saltier, it sinks in the North Atlantic, forming deep water that flows southward along the ocean floor. Eventually, this deep water upwells elsewhere, returning to the surface and completing a loop that can take hundreds or even thousands of years. This circulation has profound consequences. It moderates climate. It keeps regions like Western Europe warmer than they would otherwise be at similar latitudes. It influences rainfall patterns across continents. It shapes marine ecosystems by transporting nutrients and oxygen. If this system were to slow or change significantly, the effects would not be local. They would ripple outward, altering weather, sea level, and biological productivity across much of the globe. This sensitivity is one reason scientists pay close attention to changes in ocean circulation under current warming trends. The circulatory analogy becomes stronger when you consider what oceans transport besides heat. They carry dissolved gases, including carbon dioxide and oxygen. They move nutrients that support plankton growth. They transport organic matter from surface waters to the deep sea. In doing so, they connect life at the surface with processes far below. Phytoplankton, tiny photosynthetic organisms drifting near the surface, play a role similar to leaves in forests. They draw carbon dioxide from the air and release oxygen. When they die, some of their remains sink, carrying carbon into deeper waters. This process, known as the biological pump, helps regulate atmospheric carbon over long timescales. Circulation determines where this pump is most effective. Regions of upwelling bring nutrient-rich deep water to the surface, fueling plankton blooms. Downwelling regions carry surface water downward, transporting carbon into the depths. The balance between these processes influences how much carbon remains in the atmosphere. Again, this is not a static situation. Changes in temperature, ice cover, and wind patterns alter circulation. As the ocean warms, stratification increases. Warm surface layers become more resistant to mixing with cooler, deeper waters. This can reduce nutrient supply to the surface, weakening biological productivity in some regions. It can also reduce oxygen levels at depth, stressing marine life adapted to narrow conditions. These responses illustrate an important point. Circulatory systems are not just pathways, they are regulators. When flow changes, the distribution of resources changes. Some areas receive less, others receive more. The consequences are systemic. Oceans also act as buffers. They absorb vast amounts of heat, slowing the pace of atmospheric warming. More than 90% of the excess heat generated by greenhouse gas emissions has gone into the oceans. This has delayed some surface warming, but it has not removed the energy. It has redistributed it. As oceans absorb heat, they expand. Sea levels rise. Warmer water also affects ice sheets, melting them from below where ice meets ocean. These changes feed back into circulation patterns, altering currents and further redistributing heat. The buffering capacity of oceans is impressive, but it is not unlimited. Just as a circulatory system can compensate for stress up to a point, beyond certain thresholds its function can degrade. The analogy is not perfect, but it is instructive. Systems designed by evolution or physics to maintain balance often do so within bounds. Push beyond those bounds, and behaviour changes. There is also the matter of timing. Ocean circulation operates slowly compared to atmospheric processes. This slowness can be stabilising. It smooths out short-term fluctuations. It also means that changes once initiated can persist long after the original cause has passed. Heat stored in the deep ocean today will influence climate decades from now. This delayed response complicates cause and effect. Actions taken now shape conditions far into the future. Conversely, current conditions reflect choices and processes set in motion long ago. The ocean carries memory in the form of heat, salinity, and chemical composition. This memory is layered. Surface waters reflect recent conditions. Deeper waters reflect older states of the climate. Some deep waters have not been in contact with the atmosphere for centuries. They carry signatures of past temperatures and gas concentrations. When they eventually resurface, they influence present conditions. This temporal layering reinforces the sense of oceans as more than containers. They are active participants in Earth's long-term regulation. They integrate signals over time, storing and releasing them according to physical constraints rather than human schedules. The circulatory metaphor also helps explain why disruptions can have widespread effects. Consider the addition of fresh water from melting ice. Fresh water is less dense than salty water. When large amounts of it enter the ocean, particularly in regions where deep water formation occurs, it can inhibit sinking. This can slow or alter circulation patterns. Such changes have occurred in the past. Paleoclimate records show periods when circulation weakened or reorganized, coinciding with abrupt climate shifts. These events were not caused by a single factor, but by accumulations of change that pushed the system past a threshold. Understanding these past shifts helps frame current concerns. It shows that circulation is resilient but not immutable. It can adjust gradually or shift suddenly depending on circumstances. Another aspect of ocean circulation that deepens the analogy is connectivity. No part of the ocean is truly isolated. Water that sinks in one region eventually influences conditions elsewhere. Pollutants released near coasts can be transported far from their source. Nutrients from one basin can affect productivity in another. This connectivity challenges the idea of local impact. Actions taken in one place propagate through the system. The ocean does not respect political boundaries. Its circulation links distant regions into a single dynamic whole. This realization has reshaped marine science. Researchers increasingly study ocean basins as interconnected components rather than separate entities. Models track flows across entire hemispheres. Observations from satellites, floats, and deep-sea instruments are integrated to capture the full picture. As data accumulates, the image that emerges is not of water sloshing aimlessly, but of structured movement governed by physical laws that produce coherent patterns. Patterns that stabilize climate, patterns that support life, patterns that respond to disruption. These patterns do not require a central controller. They arise from gradients and constraints. Heat moves from warm to cold. Density differences drive motion. Rotation shapes pathways. The resulting circulation is an emergent property of the system. Emergence is key here. It describes how complex behavior arises from simple rules without design or intention. Circulatory flow is not planned. It is inevitable given the conditions, and yet its effects are coordinated in ways that resemble the function of a living system. This resemblance is what makes the ocean such a compelling piece of the larger question. When multiple Earth systems exhibit behavior that maintains conditions for life, responds to disturbance, and integrates changes over time, the boundary between inert and active becomes less clear. The ocean does not care about life, but life depends on the ocean caring about physics. That distinction matters. It keeps the discussion grounded. The system does not act for a purpose. Purpose emerges for those who rely on the outcome. For humans, this dependence is increasingly apparent. Fisheries rely on circulation to deliver nutrients. Coastal communities rely on it to moderate climate. Global weather patterns depend on heat distribution mediated by currents. When circulation changes, these dependencies are exposed. Regions accustomed to stable conditions experience new variability. Extremes become more frequent. Predictability decreases. These changes are often described as external threats, but they are better understood as internal responses. The system is adjusting to new inputs. Greenhouse gases alter heat balance. Ice melt alters salinity. The ocean responds accordingly. This framing shifts responsibility without assigning blame. It recognizes that actions feed into systems that answer back, not with intent, but with consequence. As this perspective settles, the ocean begins to feel less like a backdrop and more like a moving organ. Not alive in itself, but essential to the functioning of the whole. Its currents become pathways of exchange. Its depths become reservoirs of memory. Its surface becomes an interface between air and water. This does not diminish the mystery of the sea. If anything, it deepens it. Understanding circulation reveals structure, but not simplicity. It shows how much is happening beyond immediate perception, how much depends on slow movement and delayed response. For now, staying with the ocean is enough. With the steady movement of water across basins, with the transport of heat and carbon, with the realization that beneath the surface of apparent stillness lies a circulation that touches every shore, every climate, every breath taken on land. That movement does not ask to be noticed. It continues regardless. But once seen, it becomes difficult to think of the planet as something that simply sits there. The oceans are always moving, always connecting, always carrying the signals of change forward. And in that motion, the idea of Earth as an active system grows harder to ignore. From a distance, the surface of the Earth looks solid, settled, finished. Continents appear fixed. Mountains seem permanent. Land feels like the most reliable thing there is, the one part of the planet that does not move beneath our feet unless something goes very wrong. This sense of stability is so convincing that it shaped human thinking for most of history. The ground was assumed to be static, a foundation upon which everything else happened. That assumption only begins to unravel when you stretch your sense of time far beyond a human lifetime. Not centuries, but millions of years. When time expands that way, the crust stops behaving like a rigid shell and starts behaving like something far more dynamic, something that shifts, folds, fractures, melts, and reforms. Something that is never finished, even when it appears still. The Earth's crust is thin compared to the planet's overall size. If Earth were reduced to the size of an apple, the crust would be thinner than the apple's skin. Beneath it lies the mantle, hot and slowly flowing over geological timescales. That slow flow is not dramatic. It does not surge or churn in ways we would recognize. It creeps, millimeter by millimeter. But over millions of years, that creeping motion becomes powerful enough to rearrange continents. The crust is broken into plates, not cleanly, not neatly, but into vast slabs of rock that float atop the mantle. These plates move relative to one another, pushed by heat rising from below and pulled by their own weight as colder, denser sections sink. The motion is slow, about the speed fingernails grow, but it never stops. This alone begins to challenge the idea of Earth as inert. Objects do not move internally without external force. They do not rearrange themselves from the inside out. Earth does, driven by energy left over from its formation, and continuously replenished by radioactive decay deep within. Where plates meet, the planet becomes expressive. At some boundaries, plates pull apart. Magma rises to fill the gap, creating new crust. At others, plates collide. One may buckle upward, forming mountains. Another may sink back into the mantle, recycled rather than preserved. In still other places, plates slide past one another, building tension that is released in earthquakes. These processes are not occasional, they are constant. Even when no earthquake is felt and no volcano erupts, the forces are still at work. Stress accumulates, rock deforms, heat migrates. The crust is never truly at rest. The language we use to describe these processes often sounds mechanical. Plates, boundaries, forces. But the behaviour itself is not machine-like in the everyday sense. Machines wear down. They do not rebuild themselves. Earth's crust does both. Old crust is destroyed. New crust is created. Mountains rise and erode. Sediment accumulates and lithifies into rock. That rock may later melt, reform and emerge again somewhere else. This cycle has no endpoint. There is no final arrangement the planet is working toward. The crust rearranges itself because energy continues to move through the system. Heat escapes. Gravity acts. The result is ongoing transformation. What makes this particularly striking is that the crust does not only break and build, it also heals. After an earthquake, faults may slowly lock again. After a volcanic eruption, new land cools and stabilizes. After mountain-building events, erosion redistributes material, smoothing extremes and filling lowlands. Healing here does not mean returning to a previous state. It means settling into a new configuration that can persist for a time. Time, again, is the key. On human timescales, these changes feel catastrophic or negligible. A sudden earthquake devastates a city. A slow uplift goes unnoticed. But on planetary timescales, both are expressions of the same system adjusting stress and energy. There is also feedback between the crust and other Earth systems. Mountain ranges influence climate by altering wind patterns and precipitation. They create rain shadows. They guide rivers. Those rivers in turn erode the mountains, carrying sediment to the oceans. That sediment may eventually become rock again, perhaps uplifted in a future collision. Ice plays a role as well. During ice ages, massive ice sheets press down on the crust, depressing it. When the ice melts, the land slowly rebounds, rising over thousands of years. This process, called isostatic adjustment, is still happening in places once covered by glaciers. The crust remembers weight. It responds slowly, patiently, long after the immediate cause has vanished. This memory-like behaviour complicates the object metaphor further. Objects do not respond long after forces are removed. Systems do. The crust carries imprints of past conditions that shape its present behaviour. The crust also participates in chemical exchange. Weathering breaks rock down, releasing minerals into soil and water. These minerals nourish plants, influence ocean chemistry, and affect atmospheric carbon levels. Chemical weathering draws carbon dioxide from the air, locking it into carbonate minerals. Over long periods, this process helps regulate climate. Again, this is not intention. It is consequence, but consequence that operates reliably enough to matter. The crust is not just a surface. It is an active participant in planetary regulation. Volcanoes illustrate this vividly. They are often framed as destructive forces, and locally they are. Lava flows destroy ecosystems. Ash clouds disrupt air travel. But volcanism is also how the planet releases internal heat and gases. Volcanic eruptions add carbon dioxide to the atmosphere, but they also create new land and supply nutrients. Volcanic soils are among the most fertile on Earth. Over geological timescales, volcanism balances other processes. Carbon released by volcanoes is eventually drawn down by weathering and biological activity. The timing may be uneven, the balance imperfect. But without volcanism, the planet would cool, tectonics would slow, and many of the processes that support life would falter. This interplay between destruction and creation is a recurring theme. The crust does not preserve landscapes indefinitely, it transforms them. What feels like loss at one scale becomes input at another. Mass extinctions often coincide with major tectonic or volcanic events. Large igneous provinces, where massive amounts of lava erupt over relatively short geological periods, have been linked to dramatic climate shifts and biodiversity loss. These events are catastrophic from the perspective of existing life. But life does not end. It reorganizes, new species emerge, new ecosystems form. The crust, in this sense, sets the stage for evolutionary change. By rearranging continents, altering sea levels and modifying climate, it creates new selective pressures. Life responds. The planet and its inhabitants change together. This co-evolution reinforces the sense that Earth systems are not independent. The crust influences life. Life influences weathering and sedimentation. Sediments influence tectonics by altering crustal thickness and weight. The loop closes. Once these connections are seen, the idea of Earth as a static object becomes increasingly difficult to maintain. Objects do not recycle themselves. They do not generate novelty through internal processes. They do not integrate feedback across such disparate domains. The crust also challenges our sense of permanence. Cities feel enduring, borders feel fixed. But on geological timescales, they are fleeting. Coastlines shift, continents drift. What is land today may be seabed tomorrow. What is stable now may fracture later. This impermanence is not chaos. It follows rules. Plate motions are constrained by physics. Stress accumulates in predictable ways. Erosion follows gradients. But predictability does not mean stasis. It means change unfolds within bounds. Understanding this has reshaped how scientists think about Earth hazards. Earthquakes are not random. They follow fault lines shaped by long-term plate motion. Volcanic eruptions occur where conditions favour magma ascent. Landslides follow patterns of slope, material and moisture. Risk, then, is not simply bad luck. It is the intersection of human settlement with ongoing planetary processes. The crust does what it has always done. Humans are the variable. This perspective can feel unsettling. It undermines the idea of control. It suggests that safety is conditional, dependent on alignment with processes far larger than ourselves. But it can also be clarifying. It shifts the focus from domination to accommodation. Seeing the crust as dynamic invites a different relationship with land. Not one of fear, but one of respect for timescales and forces beyond immediate perception. It encourages planning that accounts for movement rather than assuming permanence. There is also something quietly remarkable about the fact that the crust heals at all. Faults lock, landscapes stabilise. After disturbance, the system does not remain in perpetual crisis. It finds new configurations. Stability is not the absence of change. It is the ability to absorb change without losing coherence. This is another property often associated with living systems: resilience. The capacity to reorganize while retaining function. The crust exhibits this, not through biology, but through physics and chemistry operating over time. That distinction matters. Calling the crust alive in a literal sense would be misleading, but recognizing that it behaves in ways that support ongoing planetary function is accurate. It participates in cycles, it responds to stress, it contributes to regulation. As the picture grows more complete, the planet begins to feel less like a backdrop and more like an ongoing process. Forests exchange gases, oceans move heat. The crust shifts and rearranges itself, setting conditions for everything else. Each system operates according to its own rules, yet none operate alone. The crust shapes ocean basins. Ocean circulation influences climate. Climate affects weathering and erosion. Weathering alters crustal chemistry. The loops multiply. None of this requires intention. None of it requires awareness. But together it creates a planet that behaves less like an object and more like a self-modifying system. This realization does not demand awe. Though awe may arise naturally, it demands attention. Attention to scale, attention to connection. Attention to the fact that the ground beneath us is not a finished product, but a temporary arrangement in a much longer story. For the moment, it is enough to linger on the crust, on the slow creep of plates, on the rise and fall of mountains, on the quiet healing that follows rupture, on the idea that even the most solid part of our world is participating in a continuous process of change. The ground beneath you tonight feels still, and for your purposes, it is. But beneath that stillness lies motion that has never stopped. Motion that rearranges the planet piece by piece, setting the conditions for everything that comes next without ever needing to announce itself. Weather is usually introduced to us as information, a forecast on a screen, icons of clouds and suns, numbers that tell us how to dress, whether to carry an umbrella, or if travel might be delayed. It is framed as something external and temporary, a background condition that passes over us and then moves on. Tomorrow's weather replaces today's. The story resets every morning. That framing is convenient, but it hides something important. Weather is not just a sequence of isolated events. It is the visible expression of energy moving through the planet. It is how Earth redistributes heat, moisture, and momentum from places of excess to places of deficit. When you begin to look at it this way, weather starts to feel less like a series of forecasts and more like a signalling system. Not a nervous system in a biological sense, but something that plays a similar role. A fast, responsive network that transmits changes across the surface of the planet. Unlike oceans or tectonic plates, weather operates on human timescales. Hours, days, seasons. That immediacy makes it feel personal. A storm disrupts plans, a heat wave strains bodies, a cold snap bites through clothing. Weather is how the planet touches us most directly, which may be why it is often treated as capricious or moody. But beneath that apparent unpredictability lies structure. The atmosphere is thin. If Earth were the size of a classroom globe, the layer of air we live in would be thinner than a coat of varnish. And yet, within that thin layer, vast amounts of energy circulate continuously. Sunlight heats the surface unevenly. The equator receives more energy than the poles. Land heats and cools faster than water. Ice reflects sunlight while darker surfaces absorb it. These differences create gradients, and gradients drive motion. Air moves because it is pushed by imbalance. Warm air rises, cold air sinks, pressure differences develop. Wind flows from high pressure to low, deflected by the planet's rotation. Moisture evaporates, condenses, releases latent heat, and fuels further motion. Each of these steps follows physical laws. None are random. Together they form patterns that repeat, shift, and interact. This is where the nervous system analogy begins to make sense. In a body, nerves transmit signals rapidly. They respond to stimuli. They coordinate responses across different regions. The atmospheric circulation does something similar, though without neurons or awareness. A change in one region affects conditions elsewhere. Heat buildup in the tropics influences jet streams. Sea surface temperatures alter storm tracks. Snow cover affects pressure systems. Weather communicates the state of the planet's surface upward into the atmosphere, and then outward across the globe. It is feedback made visible. Consider storms. A storm is not just rain and wind. It is a mechanism for moving heat and moisture. Tropical storms form over warm ocean water because that warmth provides energy. As the storm develops, it lifts heat from the surface and transports it upward and outward. In doing so, it cools the ocean beneath and redistributes energy into the atmosphere. From a human perspective, storms are disruptive. From a planetary perspective, they are functional. They relieve imbalances. They move excess energy away from regions where it has accumulated. Without storms, heat would build unevenly, and temperature gradients would become more extreme. This does not mean storms are good or bad. It means they have a role. Assigning moral value to weather misses the point. Weather is a response, not an intention. The same is true for droughts. Drought is often framed as absence, lack of rain, failure of weather. But drought is also a pattern. It emerges from persistent atmospheric configurations that block moisture transport. High-pressure systems stall. Jet streams shift. Moisture is diverted elsewhere. The system is still active. It is just channeling energy differently. These persistent patterns are especially revealing. When weather becomes stuck, repeating itself over weeks or months, it signals something deeper than day-to-day variability. Blocking highs, prolonged heat waves, extended wet or dry periods all reflect changes in large-scale circulation. As the planet warms, these patterns are shifting. Temperature differences between the poles and equator are changing. Arctic warming reduces that gradient, which can weaken and meander the jet stream. A slower, more sinuous jet stream allows weather patterns to linger. Heat waves last longer, storms stall, extremes intensify. This is not coincidence. It is the atmosphere responding to altered boundary conditions. Weather is the messenger. It carries the signal of deeper change to the surface where it becomes impossible to ignore. In biological nervous systems, signals are not constant. They spike in response to change. Pain, for example, is not a continuous sensation. It is a response to injury or imbalance. Weather extremes function in a similar way. They draw attention to stress within the system. This comparison is imperfect, but instructive. It highlights the speed and sensitivity of atmospheric processes compared to slower Earth systems. Oceans move heat slowly. Ice responds over decades. Tectonics unfold over millennia. Weather reacts in real time. Because of this speed, weather often appears chaotic. Small changes can produce different outcomes. Forecasts lose accuracy beyond certain horizons. This sensitivity is sometimes called chaos, but chaos does not mean randomness. It means the system is highly sensitive to initial conditions. Sensitive systems are often excellent messengers. They amplify small changes, making them visible. Weather does this constantly. Slight changes in sea surface temperature can alter storm intensity. Minor shifts in wind patterns can redirect rainfall. These responses allow the atmosphere to act as an early indicator of broader shifts. Seen this way, weather is not noise-obscuring climate signals. It is how those signals propagate. The distinction between weather and climate is often emphasized to avoid confusion. Weather is what happens day to day. Climate is the statistical pattern over time. This distinction is useful, but it can also create artificial separation. Weather is how climate expresses itself moment by moment. Climate is the accumulated behavior of weather. Ignoring weather as mere short-term fluctuation risks missing how the system is adjusting. Patterns in extremes, frequency, and persistence matter. They tell us how energy flows are changing. Clouds offer another example of atmospheric sensitivity. Clouds reflect sunlight, cooling the surface, but they also trap heat, warming it. The balance depends on cloud type, altitude, and coverage. Small changes in cloud behavior can significantly affect climate. Cloud formation depends on aerosols, tiny particles in the air from natural sources like dust and sea spray, as well as human activities like combustion. Changes in aerosol concentration influence cloud properties, which in turn influence radiation balance. This creates feedbacks that are still not fully understood. The atmosphere, in this sense, is constantly integrating signals from the surface. It responds to vegetation changes, ocean temperatures, ice cover, and even urbanization. Cities create heat islands that alter local circulation. Large-scale land use changes affect regional weather. Weather, then, is not separate from the surface. It is coupled to it. The atmosphere listens, in a physical sense, to what is happening below and responds accordingly. This responsiveness becomes especially clear during seasonal transitions. As sunlight shifts with Earth's orbit, pressure systems migrate, monsoons develop, winds reverse direction. These changes are not arbitrary. They are large-scale adjustments to seasonal energy redistribution. Monsoons, in particular, illustrate how weather acts as a coordinated system. They are not simply rainy seasons. They are driven by differential heating between land and ocean. As land heats faster, air rises, drawing in moist air from the sea. Rain follows. When the land cools, the pattern reverses. These cycles support agriculture, ecosystems, and water supplies for billions of people. Disruptions to monsoon patterns have immediate consequences. Again, weather is not a background feature, it is an active regulator. In this context, calling weather a nervous system does not imply consciousness. It implies connectivity and speed. It highlights how quickly the planet responds to imbalance at its surface. The analogy also helps explain why weather can feel overwhelming. Nervous systems respond rapidly to stress. When a system is under sustained strain, signals become more intense and frequent. Pain increases, sensitivity rises. The same appears to be happening with weather extremes under current warming trends. Heat waves are becoming more intense. Heavy rainfall events are increasing in many regions. Storms are carrying more moisture. These changes align with physical expectations. Warmer air holds more water vapor. More energy fuels stronger events. The atmosphere is doing what it always does. It is responding to energy imbalance. The difference is the magnitude and rate of change. From this perspective, extreme weather is not misbehavior. It is communication. It tells us that the system is adjusting rapidly. Whether those adjustments stabilize or destabilize conditions depends on many interacting factors. This framing can be uncomfortable. It removes the illusion that weather is something separate we can simply endure or avoid. It places weather within the same web of interaction as forests, oceans, and crust. It also complicates responsibility. We do not control weather directly, but we influence the conditions it responds to. Altering atmospheric composition changes how the system behaves. Weather is the visible outcome. In biological systems, ignoring signals often worsens outcomes. Pain that is suppressed rather than addressed can lead to further injury. This analogy should not be pushed too far, but it suggests a similar principle. Weather extremes indicate stress. Addressing underlying causes matters more than managing symptoms. Weather also connects distant regions rapidly. A disturbance in one part of the system can propagate elsewhere within days. Dust from deserts crosses oceans. Smoke from fires affects air quality thousands of kilometers away. Volcanic eruptions alter global temperatures for years. These connections reinforce the sense that the atmosphere is a global network rather than a local feature. It transmits information quickly, linking the planet's surface into a single dynamic system. Understanding weather this way also changes how we interpret variability. Not every extreme event is caused by climate change, but the probability and intensity of extremes are shifting. The baseline is moving. The nervous system is operating under new conditions. This does not mean predictability disappears. It means predictions must account for altered patterns. Models improve as understanding deepens. Observations refine theory. The system remains complex but not unknowable. Weather's role as a fast responder makes it an early indicator. Changes appear there first before slower systems fully adjust. Ice melt lags. Ocean circulation lags. Vegetation changes lag. Weather reacts immediately. That immediacy can feel relentless. But it also offers opportunity. Signals received early allow for adjustment. Ignoring them delays response until slower, harder to reverse changes occur. As this perspective settles, weather begins to feel less like an annoyance and more like a conversation. Not a conversation with intent or language, but with cause and effect. Energy flows, the atmosphere answers, patterns shift. This does not require personifying storms or attributing meaning to lightning. It requires recognizing that the atmosphere is not passive. It is an active component of the Earth system, transmitting and amplifying change. It is enough to notice how weather behaves, not as isolated events, but as expressions of a connected system. The next time you check a forecast, consider it not just information, but a snapshot of energy in motion, a glimpse of how the planet is redistributing heat and moisture in response to its current state. The clouds moving overhead, the wind shifting direction, the rain beginning or ending, these are not random acts. They are the surface expression of a deeper process, one that connects continents and oceans in near real time. Weather does not think, it does not feel, but it responds. And in that responsiveness, it plays a role strikingly similar to a nervous system, carrying signals rapidly across a living planet that is constantly adjusting to itself. When people talk about balance in nature, it often sounds like a vague ideal rather than a concrete process. Balance is imagined as stillness, a calm state where nothing changes and everything remains comfortably the same. But that picture has very little to do with how Earth actually works. Balance on this planet is not achieved through stability, it is achieved through movement, through constant adjustment, through feedback. Feedback is one of those words that quietly explains a great deal once you stop and look at it closely. A feedback loop occurs when the output of a process influences the process itself. Sometimes that influence dampens change. Sometimes it amplifies it. Either way, the system is no longer linear. It begins to respond to its own behaviour. Living systems rely on feedback constantly. Your body temperature is regulated through feedback. Too warm and mechanisms activate to cool you down. Too cold and others activate to generate heat. The goal is not a fixed temperature down to the decimal, but a range that allows function to continue. Earth operates in much the same way, though without goals, awareness, or intent. The planet does not seek balance. Balance emerges because feedbacks constrain extremes. When those constraints weaken or reverse, balance shifts or breaks. One of the simplest examples lies in ice and sunlight. Ice reflects sunlight. Dark surfaces absorb it. When temperatures drop and ice spreads, more sunlight is reflected, reinforcing cooling. When temperatures rise and ice melts, darker surfaces are exposed, absorbing more heat and reinforcing warming. This is a positive feedback loop. It amplifies change. Positive does not mean good. It means reinforcing. These loops can push a system rapidly toward a new state once a threshold is crossed. Earth's history contains many examples of this. Ice ages deepened as ice spread. Warm periods intensified as ice retreated. But positive feedbacks are only half the story. Negative feedbacks counteract change, they stabilize. The most important long-term stabilizer of Earth's climate involves rock, rain, and carbon dioxide. When temperatures rise, chemical weathering of rocks increases. Rainwater reacts with carbon dioxide to form weak acids that break down rock. This process removes carbon dioxide from the atmosphere and locks it into minerals. Over long timescales, this reduces greenhouse warming and cools the planet. When temperatures fall, weathering slows. Volcanic activity continues releasing carbon dioxide, allowing greenhouse gases to accumulate and warm the planet again. This feedback operates over millions of years. It is slow, but powerful. It is one reason Earth has remained habitable for so long despite changes in solar output. What matters here is not perfection, but persistence. Balance is dynamic. It is maintained by opposing tendencies that rarely cancel each other exactly. The planet oscillates within bounds, sometimes drifting closer to limits, sometimes pulled back. These feedbacks exist across systems. Forests regulate atmospheric gases. Oceans absorb heat and carbon. Ice reflects energy. Weather redistributes heat. The crust cycles materials. None of these systems act alone. Feedbacks cross boundaries. For example, warming increases evaporation. More water vapor enters the atmosphere. Water vapor is itself a greenhouse gas, which enhances warming. That is a positive feedback. But increased evaporation can also lead to more cloud formation. Depending on cloud type and altitude, clouds may reflect sunlight and cool the surface, acting as a negative feedback. The net effect depends on context. This complexity is why simple cause and effect thinking often fails at planetary scale. Feedbacks overlap. Some dominate in certain conditions, others dominate elsewhere. The balance shifts. Self-correction arises when negative feedbacks are strong enough to counteract disturbances. It does not mean the system returns to its original state. It means it finds a new configuration that functions within constraints. After a forest fire, vegetation regrows. The species mix may change. Soil properties may shift, but plant cover often returns, stabilizing soils and restoring gas exchange. That is self-correction, not restoration. After a mass extinction, biodiversity rebounds over millions of years. New species emerge, ecosystems reorganize. The planet does not recreate what was lost. It creates something new that works under new conditions. This distinction is important. Self-correction is not conservation. It is adaptation. Human expectations often confuse the two. We hope systems will return to familiar states. Earth is not obligated to comply. Its feedbacks do not aim to preserve specific outcomes. They aim to dissipate energy and maintain flow. Understanding this helps explain why some changes feel irreversible. Once a feedback loop pushes the system past a threshold, returning to the previous state may require conditions that no longer exist. Ice sheets, once melted beyond a point, may not regrow easily even if temperatures drop. Forests, once replaced by grassland under new climate regimes, may not return without intervention. Feedbacks create path dependence. History matters. The order and timing of changes influence what becomes possible next. This does not mean Earth is fragile in a simplistic sense. It means resilience operates at system level, not component level. Individual species vanish. Landscapes transform. The overall system persists. From a human perspective, this can feel unsettling. We prefer stability we recognize. Earth's version of balance is indifferent to familiarity. It tolerates change as long as flows continue. Feedback loops also explain why small changes can sometimes have outsized effects. A gradual increase in temperature may produce little visible change until a threshold is crossed. Then feedbacks accelerate transformation. This nonlinear behavior surprises those expecting proportional response. Lakes suddenly become eutrophic. Ice shelves collapse. Circulation patterns reorganize. These are not sudden failures. They are delayed responses to accumulated pressure. In engineering, systems with feedbacks are carefully designed to avoid runaway behavior. Earth has no designer adjusting dials. Its feedbacks arise from physics, chemistry, and biology interacting over time. Most of the time, these interactions constrain extremes. Sometimes they amplify them. The idea of self-correction often leads to complacency. If Earth corrects itself, the thinking goes, then disturbances do not matter. This misses a crucial point. Self-correction operates on planetary timescales, not human ones. The system may correct in ways incompatible with current civilizations. The planet does not guarantee comfort, it guarantees continuity. This reframing changes how responsibility is understood. Humans cannot break Earth in an absolute sense, but we can push it into states that are hostile to us. Feedbacks will still operate. Balance will still emerge. But the resulting balance may exclude conditions we depend on. Seen this way, environmental concern is not about saving the planet. It is about negotiating our place within its feedbacks. The more we understand these loops, the clearer it becomes that no single action determines outcome. Cumulative effects matter. Interactions matter. Delays matter. Feedbacks also explain why solutions focused on one variable often fail. Reducing one emission source may not stabilize climate if other feedbacks continue to amplify warming. Restoring one ecosystem may not succeed if surrounding conditions remain degraded. This does not imply futility, it implies systems thinking. Effective action aligns with feedbacks rather than fighting them blindly. Agricultural practices that build soil carbon work with feedbacks. Soils store carbon, improve water retention, and support plant growth, which further stabilizes soils. This is self-reinforcing in a stabilizing direction. Urban heat islands illustrate the opposite. Paving increases heat absorption. Higher temperatures increase energy demand for cooling. Waste heat further warms the area. This feedback amplifies discomfort and risk. The planet is full of such loops. Some are ancient, some are new. Human activity has introduced feedbacks that did not exist before or has strengthened ones that were previously weak. Plastic pollution alters marine ecosystems. Nitrogen runoff creates dead zones. Atmospheric aerosols change cloud behaviour. Each of these interacts with existing loops in ways that are still being unravelled. What stands out is that Earth does not behave as a collection of independent problems. It behaves as a network of feedbacks constantly adjusting to energy flows. Balance, then, is not a static goal. It is a moving range defined by what feedbacks allow. Self-correction is not moral or intentional. It is mechanical in the deepest sense, though the mechanisms span biology, chemistry, and physics. Calling this alive may or may not be useful, but calling it inert is inaccurate. As this picture settles, the planet begins to feel less like something that can be fixed with a single solution, and more like something that must be understood in motion. Decisions become about direction rather than control, about steering within limits rather than commanding outcomes. The question shifts from how to stop change to how to influence which feedbacks dominate, which loops are strengthened, which are weakened. This is not abstract. It plays out in land use, energy systems, food production, and urban design. Each choice feeds into loops that extend beyond immediate surroundings. Feedbacks do not judge, they respond. Balance does not negotiate, it emerges. Recognizing this does not remove agency, it clarifies it. Agency exists in shaping inputs, not dictating outputs. Earth adjusts to itself continuously, sometimes gently, sometimes abruptly, always according to the rules set by energy, matter, and interaction. Balance is not something the planet has, it is something the planet does. There comes a point in this story where the ideas we've been circling begin to gather around a name. Not because naming them makes them more true, but because humans tend to feel more comfortable once something has a label. Patterns, feedbacks, self-regulation, atmospheric balance, oceans moving heat, forests exchanging gases, crust recycling itself. Individually, these observations were uncontroversial. Together, they began to suggest something that made many scientists shift uneasily in their chairs. In the 1970s, a chemist named James Lovelock was working with NASA, helping design experiments to detect life on Mars. One of the simplest ideas he explored was this: if a planet hosts life, its atmosphere should look strange, not chemically relaxed, not settled into equilibrium. Life, by its nature, disrupts chemical balance. It produces gases, consumes others, and maintains mixtures that would otherwise react away. When Lovelock looked at Earth's atmosphere, he saw exactly that. Oxygen coexisting with methane, nitrogen present in large quantities, gases that, left alone, should not persist together for long. Their continued coexistence implied constant replenishment, constant activity. By contrast, when he examined Mars and Venus, their atmospheres looked chemically quiet. Carbon dioxide dominated. Little variation, no obvious sign of continual disturbance. This contrast led to a simple but unsettling thought. Earth's atmosphere might not just host life, it might be shaped by it in a way that helps maintain conditions suitable for life itself. Working with microbiologist Lynn Margulis, Lovelock developed this idea further. Together, they proposed what became known as the Gaia hypothesis. The core suggestion was not that Earth is conscious or intentional or aware. It was that life and the physical environment are tightly coupled, forming a self-regulating system that maintains conditions favourable for life over long periods. On paper, this sounds like a straightforward extension of feedback thinking. In practice, it triggered immediate discomfort. Part of the unease was the name. Gaia, drawn from Greek mythology, was the personification of Earth. To many scientists, this sounded dangerously close to mysticism. It evoked images of a thinking planet, a nurturing mother figure, an idea more at home in poetry or spirituality than in laboratories. Lovelock himself later admitted that the name may have been a mistake, suggested half-jokingly by a friend. But the reaction revealed something deeper than discomfort with language. It exposed an anxiety about boundaries. Where does science end and metaphor begin? When does systems thinking slide into anthropomorphism? The hypothesis challenged a deeply ingrained assumption that environments shape life, but life does not shape environments at planetary scale in a coordinated way. Ecology had already complicated that assumption at local scales. Gaia extended the complication globally. Critics worried that the idea implied purpose, that it suggested Earth somehow wanted to maintain life, that it smuggled teleology back into science through the back door. Science, particularly in the 20th century, had worked hard to remove purpose from natural explanation. Lovelock insisted that no purpose was required. Self-regulation could emerge without intention. Feedbacks could stabilize systems automatically. But the suspicion lingered. To make the idea more concrete, Lovelock proposed a simple model called Daisy World. It imagined a planet orbiting a star covered only by black and white daisies. Black daisies absorbed heat. White daisies reflected it. As the star's brightness changed, the relative abundance of each type shifted, regulating the planet's temperature over a wide range. No daisy intended to regulate climate. Each simply grew better under certain conditions, yet the combined effect was temperature stabilization. Daisy World demonstrated that self-regulation could arise from natural selection, acting locally, without foresight or design. This was a crucial point. Gaia did not require cooperation. It did not require global awareness. It required only that life alter its environment in ways that feed back on life's own survival. Despite this, skepticism remained strong. Many biologists argued that natural selection operates at the level of individuals or genes, not planets. Why would traits that benefit global stability be favoured if they do not directly benefit individual organisms? This criticism forced the hypothesis to evolve. Early formulations of Gaia were broad and provocative. Later versions became more restrained, focusing on specific feedback mechanisms rather than global harmony. Scientists began reframing the idea in terms of Earth system science. Instead of asking whether Earth behaves like an organism, they asked how tightly coupled systems interact. Atmosphere, biosphere, hydrosphere, lithosphere. The language changed. The discomfort lessened slightly. Even so, unease persisted. Not because the data contradicted the idea, but because the idea sat awkwardly with reductionist habits of thought. Systems that regulate themselves without controllers challenge intuition. They blur lines between cause and consequence. One reason Gaia felt threatening was that it undermined the notion of human exceptionalism. If Earth already possesses powerful self-regulating feedbacks, then humans are not external managers. We are participants, inputs, not overseers. Another reason was methodological. Science prefers hypotheses that can be tested cleanly. Gaia, as a broad framework, resisted simple falsification. It was not a single prediction, but a lens through which many processes could be interpreted. That made it harder to accept within traditional scientific norms. Over time, however, parts of Gaia quietly became mainstream without the name attached. Climate models incorporated biosphere feedbacks. Carbon cycle studies acknowledged the role of vegetation and oceans in regulating atmospheric composition. Earth system models treated the planet as an integrated whole. The idea survived by shedding its most provocative language and embedding itself in practice. Still, something about Gaia continued to make scientists uneasy, perhaps because it forced an uncomfortable admission that Earth behaves, in aggregate, in ways that resemble living systems more than machines. Not alive in the way a bacterium is alive, but alive in the sense of being self-modifying, responsive and historically contingent. This resemblance does not imply intention, but it does imply limitation. Living systems can fail. They can shift into states that are hostile to certain forms of life while remaining functional overall. Gaia does not promise benevolence. In fact, one of the strongest arguments against a naive interpretation of Gaia is the history of mass extinctions. Earth has repeatedly allowed, or perhaps caused, conditions that wiped out large fractions of life. If the planet were truly maintaining life for its own sake, this would be puzzling. But from a systems perspective, it makes sense. Self-regulation operates within bounds, not guarantees. When perturbations exceed those bounds, systems reorganize. Life persists, but not necessarily in familiar forms. This reframing helps dissolve some of the unease. Gaia is not a caretaker. It is not protective. It is descriptive. It describes how tightly coupled feedbacks can stabilize conditions for long periods and then abruptly shift when thresholds are crossed. The remaining discomfort may come from what Gaia implies about responsibility. If Earth is a self-regulating system, then human activity becomes part of that system's feedbacks. Not an external disturbance, but an internal force capable of altering trajectories. This challenges narratives of control. It also challenges narratives of helplessness. If humans are internal to the system, then our actions matter not because we stand above nature, but because we are embedded within it. Some scientists have proposed abandoning Gaia altogether in favour of more neutral terms: Earth system regulation, biogeochemical coupling, emergent stability. These phrases are safer. They avoid mythological baggage. They fit comfortably within academic discourse. And yet, the persistence of the Gaia idea suggests that something about it captures attention in a way technical language does not. It gestures toward wholeness, toward integration, toward the fact that understanding Earth requires stepping back far enough to see connections rather than components. Unease, in this context, may be a sign that the idea touches a boundary of scientific comfort, not because it is wrong, but because it stretches habitual ways of thinking. Science advances not only by adding data, but by revising frameworks. Copernicus made people uneasy by moving Earth from the centre. Darwin made people uneasy by dissolving fixed categories of life. Gaia makes people uneasy by blurring the line between environment and organism. Each of these shifts faced resistance not just on empirical grounds, but on conceptual ones. They required letting go of intuitions that had once felt obvious. It's important to note that Gaia is not a theory in the narrow sense. It does not offer precise equations for every process. It is a hypothesis, a guiding idea. Its value lies in prompting questions rather than closing them. Does life significantly influence planetary conditions? Yes. Does that influence feedback in ways that affect life's persistence? Yes. Do these feedbacks operate without foresight or intent? Yes. Beyond that, claims become speculative. The scientific unease surrounding Gaia has been productive. It has forced clarity. It has driven refinement. It has prevented sloppy thinking. In that sense, skepticism has strengthened rather than weakened the underlying insight. Today, few scientists would endorse the idea of Earth as a single organism. Many would accept that Earth behaves as a coupled system with emergent regulatory properties. The difference may be more about language than substance. What remains unsettled is how to think about value. If Earth self-regulates, does that absolve humans of responsibility, or does it heighten it? If balance emerges naturally, does intervention matter, or does it shape which balance emerges? Gaia does not answer these questions. It reframes them. It suggests that the planet is not a passive victim of human action, nor an infinitely resilient machine. It is a system with dynamics that can be pushed into new states, some of which may be less accommodating to us. This realization strips away comforting illusions. It leaves neither mastery nor innocence intact. As the idea settled into scientific culture, it became quieter, less provocative, more integrated. But the unease never fully disappeared, perhaps because Gaia touches something that science alone cannot resolve: how humans relate to a system they depend on but do not control. To recognize that unease is often the sign of an idea that matters. The Gaia hypothesis does not ask us to believe in a living Earth. It asks us to consider whether the planet behaves in ways that make the distinction between living and non-living less clear than we once assumed. And that question, once raised, has a way of lingering, quietly reshaping how everything else is seen. At a certain point, it becomes difficult to talk about Earth and life as separate stories running alongside one another. The deeper you look into the planet's history, the more those stories fold into a single thread. Life does not merely exist on Earth. It has altered the planet in fundamental ways, and the planet in turn has shaped what life could become, what survived, and what vanished. This relationship is not occasional or decorative. It is continuous, mutual, and irreversible. Early Earth was hostile by today's standards. The atmosphere contained little to no oxygen. The oceans were chemically different. Ultraviolet radiation reached the surface with far fewer obstacles. Life, when it appeared, was simple, microscopic, and adapted to conditions that would be lethal to most modern organisms. But even those early forms of life began changing their surroundings almost immediately. One of the most dramatic examples is oxygen. Oxygen feels essential to us now, but for early life it was a waste product. Cyanobacteria, through photosynthesis, released oxygen into the oceans and atmosphere. At first, that oxygen reacted with dissolved iron, forming rust that settled on the seafloor. Over time, those sinks filled. Oxygen began accumulating in the air. This change, known as the Great Oxidation Event, transformed the planet. It altered atmospheric chemistry. It changed ocean composition. It triggered climate shifts, including widespread cooling, and it caused mass extinctions among organisms that could not tolerate oxygen's reactivity. From one perspective, life poisoned its own environment. From another, it unlocked entirely new possibilities. Oxygen made complex metabolism possible. It allowed for larger, more energy-demanding organisms. It paved the way for multicellular life. This was not a planned transition. No organism foresaw the outcome. Local survival strategies produced global consequences. Life reshaped the planet without intending to, and the planet reshaped life in response. This pattern repeats throughout Earth's history. Plants colonized land, drawing carbon dioxide from the atmosphere and stabilizing soils. Their roots broke rock, accelerating weathering. This weathering pulled more carbon from the air, influencing climate. Forests altered rainfall patterns. They darkened the surface, affecting heat absorption. Their presence changed erosion rates, river behavior, and sediment deposition. Animals amplified these effects. Burrowing creatures mixed soils. Grazers reshaped vegetation patterns. Reef-building organisms constructed massive limestone structures that altered coastlines and ocean chemistry. Even the shells of tiny plankton accumulated over millions of years, forming chalk cliffs and deep-sea sediments. At no point did life merely adapt to a static backdrop. The backdrop itself was being rewritten continuously by biological activity. The planet responded. Shifts in atmospheric composition altered temperature and circulation. Changes in land cover influenced albedo and water cycles. New habitats emerged, others disappeared. Evolution followed these gradients. Life adapted not just to physical conditions, but to conditions created by other life. Predation, competition, cooperation, and symbiosis all evolved within environments that biology itself had modified. This entanglement challenges simple cause and effect narratives. Did the planet shape life, or did life shape the planet? The honest answer is both, happening simultaneously, with feedbacks operating across timescales. Even mass extinctions, often framed as purely destructive planetary events, fit this pattern. Large volcanic eruptions altered climate and chemistry. Asteroid impacts changed temperature and light availability. These events wiped out dominant species, but they also reset ecological landscapes. New evolutionary paths opened. Life diversified in new directions. The planet did not protect existing life forms. It created conditions that selected for different ones. From a planetary perspective, extinction is not failure. It is reorganization. This can be uncomfortable to acknowledge, especially when considering current biodiversity loss. But it underscores a crucial point. Earth's systems prioritize flow and balance, not preservation of particular outcomes. The shaping influence runs both ways even today. Humans are a clear example. Our biology reflects planetary conditions. Our oxygen-rich metabolism depends on photosynthesis. Our water balance reflects Earth's hydrological cycle. Our bones incorporate minerals weathered from ancient rock. At the same time, human activity is now altering planetary systems at a scale comparable to geological forces. We move more sediment annually than all rivers combined. We alter atmospheric composition measurably. We influence climate, ocean chemistry, and biodiversity. This does not make humans separate from the Earth system. It makes us a particularly influential component of it. The temptation is to frame this influence as unnatural. But from a systems perspective, it is simply new. The planet has experienced many transformative agents. Life itself was one. Humans are another. What matters is not whether influence exists, but how feedbacks respond. Life's influence on Earth has often stabilized conditions, but not always. Oxygen buildup triggered ice ages. Plant colonization altered carbon cycles dramatically. Reef formation changed ocean circulation. These shifts were sometimes destabilizing before new balances emerged. The same may be true now. Human activity may be pushing systems toward new states. The question is not whether Earth will respond. It will. The question is what kind of world will emerge from that response. This framing removes moral judgment from the planet itself. Earth does not punish. It responds. Feedbacks do not evaluate intent. They operate according to physical and biological rules. This can feel unsettling because it removes the idea of guaranteed alignment between life and habitability. Earth has supported life for billions of years, but not always complex life, and not always in forms recognizable to us. The planet is not obligated to remain friendly. At the same time, the deep coupling between life and Earth suggests that change is not unidirectional. Just as life has altered planetary conditions, altering those conditions alters life's trajectory. That includes us. Our technologies, economies, and cultures are built on assumptions about climate stability, resource availability, and ecological predictability. As those assumptions weaken, adaptation becomes necessary. Adaptation, however, is not just a biological process. It is social, technological, and cultural. The planet shapes what strategies succeed. Sea level rise favours some settlements and undermines others. Shifting rainfall alters agriculture. Changing temperatures affect health and infrastructure. In this sense, the planet continues shaping life, including human life, just as it always has. Recognizing this mutual shaping does not require reverence or despair. It requires realism. It asks us to see ourselves not as managers standing outside the system, but as participants embedded within it. This perspective can be uncomfortable because it limits control. It suggests that some outcomes cannot be negotiated away, but it also offers clarity. Actions feed into feedbacks. Those feedbacks shape future conditions. Choices matter because they influence trajectories, not because they command outcomes. The idea that life and planet shape each other also reframes resilience. Resilience is not about freezing systems in place. It is about maintaining capacity to respond. Life has persisted on Earth because it is adaptable. The planet has remained habitable because feedbacks have constrained extremes. When either side loses flexibility, vulnerability increases. Modern human systems often prioritize efficiency over resilience. They optimize for current conditions rather than future variability. This makes them sensitive to planetary shifts. Recognizing Earth's dynamic role highlights the need to design systems that can adjust rather than resist. It also changes how we interpret environmental limits. Limits are not arbitrary restrictions, they are boundaries defined by feedbacks. Exceed them, and the system responds in ways that may reduce available options. Historically, life that ignored planetary constraints did not persist. Species that overexploited resources declined. Ecosystems that lost balance reorganized. The planet continued. This is not a warning delivered by a conscious Earth. It is a pattern observed repeatedly. Seeing life and planet as co-shapers also dissolves the idea that humans must choose between nature and progress. Progress that aligns with planetary dynamics is more durable than progress that ignores them. This alignment does not mean minimizing impact to zero. Impact is unavoidable. It means understanding which impacts amplify destabilizing feedbacks and which support stabilizing ones. Agricultural practices that regenerate soil, for example, align with carbon and water cycles. They support productivity while strengthening feedbacks that stabilize climate. Practices that degrade soil weaken those feedbacks, leading to erosion, emissions, and declining yields. The same logic applies to energy systems, urban design, and land use. Choices can push systems toward resilience or fragility. Life shaping the planet shaping life is not a slogan. It is a description of an ongoing process. A process that has no endpoint and no moral direction, but clear consequences. This perspective also complicates the idea of stewardship. Stewardship implies oversight, but co-shaping implies participation. We do not stand above Earth holding tools. We move within it, altering conditions as we go. This does not absolve responsibility. It deepens it. Responsibility becomes about understanding interactions rather than imposing control. As this understanding settles, the earlier question about whether Earth is alive becomes less central. What matters more is whether Earth behaves as a system in which life is an active component, continuously shaping and being shaped by planetary processes. The answer to that appears to be yes. Life has never been separate from Earth's evolution. It has always been part of how the planet works. From microbes altering atmospheric chemistry, to forests influencing rainfall, from reefs building coastlines, to humans reshaping energy flows, life is woven into the planet's fabric. And the planet responds in turn, sometimes gently, sometimes abruptly, always according to its own dynamics. The world beneath and around you is not a neutral stage. It is an active participant in a long, ongoing exchange with life itself, an exchange that has shaped every breath you take, every cell in your body, and every possibility that lies ahead, whether we recognize it or not. There is a tendency, deeply ingrained, to assume that if something important is happening, it will announce itself clearly. A sound loud enough to hear, a signal obvious enough to recognize, a change dramatic enough to force attention. This assumption works well at human scale, where danger often arrives quickly and communication relies on immediacy. But Earth does not operate at that scale alone. Much of what the planet does unfolds either far below our threshold of notice or far beyond it. Some signals are too small, others are too slow. Still others are so large and constant that they fade into background noise. In all three cases, the result is the same. Change happens without being noticed until its effects accumulate into something unmistakable. This creates a peculiar problem. If Earth does communicate its state through signals, they're rarely tailored to human perception. They're expressed through chemistry, pressure gradients, population shifts, isotopic ratios, and delayed responses spread across time and space. Listening for them requires tools, patience, and a willingness to accept that meaning does not always arrive in a familiar form. Consider scale first. A single molecule of carbon dioxide added to the atmosphere does nothing noticeable. One tree cut down does not alter climate. 1 degree of ocean warming feels trivial compared to the daily variation in weather. At these scales, change looks insignificant, easy to ignore, easy to dismiss. But Earth systems do not respond to individual events, they respond to accumulation. When billions of small actions align in the same direction, thresholds are approached quietly. Feedbacks begin to shift. What was once buffered becomes amplified. By the time change becomes obvious, it has often been underway for decades. This is one reason planetary signals are so easy to miss. They rarely arrive as sudden alarms. They arrive as trends, gradual deviations from baselines that themselves are assumed to be stable. Humans are not well adapted to notice slow drift. We evolved to respond to immediate threats and opportunities. A predator approaching, a storm forming, a fire spreading. Slow changes in average temperature or atmospheric composition do not trigger instinctive concern. They require measurement and interpretation. Scientific instruments extend our senses into these domains. Thermometers detect tiny changes in temperature. Spectrometers detect trace gases. Satellites track subtle shifts in vegetation and ice cover. Without these tools, many planetary signals would remain invisible. Even with them, interpretation is challenging. Data accumulates gradually. Noise obscures patterns. Natural variability complicates attribution. It is easier to see coincidence than connection when signals are faint. At the other extreme, some signals are too large, too constant, too familiar. The daily movement of clouds, the rise and fall of tides, the seasonal greening and browning of landscapes. These are planetary processes in action, but their regularity renders them unremarkable. Because they are always present, they fade into the background. Their importance is acknowledged abstractly, but rarely felt. We notice them only when they deviate sharply from expectation. This creates a paradox. The most fundamental planetary signals are the easiest to ignore. They shape conditions continuously, but because they do so reliably, they escape attention. Weather extremes break through this indifference precisely because they violate expectation. A heat wave that lasts too long, a storm that stalls, rain that fails to arrive. These events feel like messages, even if we hesitate to interpret them as such. Yet even here, scale complicates perception. One extreme event can be dismissed as anomaly, two as coincidence. It is only when patterns emerge across regions and years that the signal becomes difficult to deny. Earth does not send messages in single events. It communicates through repetition. There is also the issue of loudness. Human activity has become a dominant source of signal in many Earth systems. Noise in this context is not sound, it is interference. Emissions, land use change, pollution, and resource extraction introduce strong, rapid signals that can overwhelm subtler ones. When human-induced change accelerates processes that were once slow, it can drown out background dynamics. Natural cycles become harder to distinguish from new trends. Baselines shift before they are fully understood. This makes it difficult to tell which signals originate from long-standing planetary behavior and which are responses to new pressures. The distinction matters because it influences expectations. Natural variability has limits. New drivers can push systems beyond familiar ranges. Another challenge lies in timing. Earth's responses are often delayed. Oceans absorb heat slowly. Ice sheets respond over decades. Ecosystems adjust over generations. The signal of cause and the signal of effect may be separated by years or centuries. This delay creates false reassurance. When change does not produce immediate consequence, it feels safe. The absence of response is mistaken for absence of effect. But in systems with inertia, silence often precedes acceleration. Deep ocean warming offers a clear example. For years, surface temperatures may rise modestly while excess heat accumulates below. The system appears stable. Then, as heat continues to build, consequences emerge in the form of altered circulation, ice melt from below, and long-term sea level rise. The signal was present all along. It simply took time to manifest in ways that were visible. There is also the matter of spatial separation. Causes and effects do not always occur in the same place. Emissions released in one region alter climate elsewhere. Deforestation changes rainfall patterns far downwind. Ocean warming in one basin affects weather on distant continents. This separation weakens intuitive connection. Humans are inclined to link cause and effect through proximity. When distance intervenes, coincidence becomes an easier explanation. Planetary signals ignore borders. They travel along currents, winds, and feedback loops. Recognizing them requires thinking in networks rather than locations. Another layer of difficulty comes from the fact that Earth signals are often expressed statistically rather than individually. No single storm proves a trend. No single drought defines a shift. Signals emerge from changes in frequency, intensity, and distribution. Statistics are not intuitive. They require aggregation. They require patience. They require trust in methods rather than senses. This makes them vulnerable to misunderstanding or dismissal, especially when conclusions challenge existing beliefs or interests. Yet this statistical nature is not accidental. It reflects the scale at which Earth operates. Systems with many interacting components rarely change in simple, linear ways. They shift in probability space before they shift in experience. The planet also produces signals through absence, species disappearing, ice thinning, glaciers retreating. These changes are quiet. They do not produce sound or spectacle. They are noticed only by those who look regularly and closely. Absence is one of the hardest signals to interpret. It lacks drama. It accumulates slowly. It requires memory. When baseline conditions shift gradually, what was once remarkable becomes normal. This phenomenon, often called shifting baselines, dulls perception. Each generation accepts the world it inherits as normal, unaware of what has already been lost. Signals fade not because they are weak, but because reference points move. The problem is not that Earth is silent. It is that its signals do not align with human expectations of communication. If Earth were alive in a way we do not understand, this mismatch would make sense. Communication does not require intention to be missed. It requires only difference in scale, medium or time scale. Signals can exist without being addressed to anyone in particular. They are expressions of state, not messages sent with an audience in mind. In that sense, Earth signals are not warnings or pleas. They are disclosures. They reveal how the system is responding to current conditions. Whether those disclosures are noticed or acted upon is not the planet's concern. This reframing removes drama. It also removes excuse. If signals are present but unnoticed, responsibility lies with perception, not with communication. The challenge, then, is learning how to listen without expecting familiarity, without expecting urgency to look like emergency, without expecting change to announce itself loudly. Science provides some of this listening capacity. Long-term monitoring, comparative analysis, modelling. These tools allow patterns to emerge from noise. They translate planetary behaviour into forms humans can interpret. But science alone is not enough. Interpretation also requires cultural readiness, willingness to accept that significance may precede discomfort. That meaning may arrive before certainty. That action may be required before consensus feels complete. Another complication is that Earth signals are often ambiguous. The same change can have multiple interpretations depending on context. Increased vegetation growth may signal carbon uptake in one region, an ecosystem stress in another. Reduced ice cover may temporarily increase biological productivity while undermining long-term stability. Ambiguity invites debate. Debate delays response. Meanwhile, processes continue. None of this implies inevitability. Systems respond to inputs. Feedbacks can be influenced. Trajectories can shift. But only if signals are recognized while options remain open. The idea that we might be too small or too loud to notice Earth signals is not an accusation. It is an observation about mismatch. Human perception evolved for immediate survival. Planetary processes operate on different terms. Bridging that gap is one of the defining challenges of the present era. It requires humility. It requires patience. It requires accepting that understanding may arrive before comfort. There is also a quieter implication. If Earth does communicate through signals rather than speech, then listening does not mean waiting for a voice. It means paying attention to patterns, trends, and absences. It means learning a language that was never designed for us. This learning is ongoing. New data reveals new signals. Old assumptions are revised. What once seemed stable reveals variability. What once seemed variable reveals structure. In this process, certainty is rare. Confidence grows slowly. This can feel unsatisfying in a world accustomed to immediate answers, but it aligns with how Earth itself operates. The planet does not rush. It accumulates. It integrates. It responds. If we miss its signals, it does not repeat them more loudly for clarity. It continues along its trajectory. Consequences unfold according to the rules already in place. This is not punishment. It is process. As attention continues to sharpen, some signals become clearer. Feedbacks become visible. Thresholds are identified. Uncertainty narrows even as complexity remains. The question then becomes less about whether signals exist and more about whether they are being heard in time to matter. Earth may be speaking constantly, not in words or warnings, but in patterns and responses. And that hearing those patterns requires adjusting our expectations, not waiting for the planet to adjust its voice. At some point in this exploration, the word itself becomes unavoidable. Alive. It lingers in the background of every observation, every comparison, every uneasy analogy. We keep circling it without quite stepping inside, partly because it carries so much baggage. Alive is a word shaped by biology, by bodies, by cells and metabolism and reproduction. It is a word that feels precise until you try to stretch it, and then it resists. Most definitions of life are practical rather than philosophical. They exist to help scientists categorize, study, and search. Life metabolizes, life reproduces, life responds to stimuli, life evolves. These criteria work remarkably well when the subject is a bacterium, a plant, or an animal. They become less helpful when scale changes. A single cell fits neatly into these definitions. A multicellular organism does too, though already the boundaries blur. Where exactly does an organism begin and end? The human body contains trillions of microbes that are not genetically human, yet are essential to survival. Are they part of the organism or residents within it? The answer depends on perspective. At the level of ecosystems, the question grows stranger. A forest metabolizes energy, cycling carbon, water and nutrients. It responds to disturbance. It grows, changes, and reorganizes. It does not reproduce as a unit in the way an organism does, but it does spread, regenerate, and evolve in composition. Is it alive, or is it merely composed of living things? Most scientific frameworks choose the latter. It is safer. It keeps categories clean. But safety is not the same as completeness. When we scale up again to the entire planet, the discomfort intensifies. Earth does not reproduce in any meaningful biological sense. It does not have DNA. It does not consume food or excrete waste in the way organisms do. By strict biological criteria, it is not alive. And yet, Earth metabolizes energy. Sunlight enters the system, heat leaves, matter cycles internally. Chemical gradients are maintained far from equilibrium. The planet responds to disturbance. It reorganizes itself. It evolves, not biologically, but structurally and chemically over deep time. The mismatch between behavior and definition raises a question that is less about Earth and more about language. Are our definitions of life descriptions of reality, or tools shaped by the scale we're used to observing? Biology emerged as a science focused on organisms. Its concepts evolved to describe entities bounded by skin, membranes, or cell walls. Planetary systems were never its intended subject. Expecting those definitions to fit seamlessly may be unreasonable. This does not mean anything complex should be called alive. That would empty the word of meaning. It means the word may be doing less explanatory work than we assume. Consider fire. Fire consumes energy. It spreads. It responds to environment. It can grow or extinguish. For a time, some thinkers speculated whether fire might be alive. It is not. It lacks internal regulation. It does not maintain itself within bounds. It destroys the conditions it depends on unless constrained. Earth behaves differently. It does not consume its own foundations indiscriminately. Its feedbacks tend to constrain extremes rather than amplify them endlessly. That distinction matters. Consider crystals. They grow. They organize matter into repeating structures. They respond to conditions. But they do not metabolize energy flows. They do not maintain far from equilibrium states dynamically. Their growth stops when conditions change. Earth does not stop. It continues cycling energy and matter as long as external input exists. The phrase "far from equilibrium" appears often in discussions of lifelike systems. Living organisms maintain states that would collapse without constant energy input. Earth's atmosphere is far from chemical equilibrium. Its surface temperature is regulated within a narrow range compared to what physics alone might predict. These are signatures of ongoing processes counteracting decay. Again, this does not imply intention. It implies sustained activity. One way to approach the question is to stop asking whether Earth is alive and start asking what properties we associate with aliveness and why. Responsiveness, persistence, self-modification, integration across parts, memory encoded in structure, sensitivity to thresholds. Earth exhibits all of these. The planet responds to changes in solar input. It adjusts atmospheric composition. It alters circulation patterns. It modifies surface reflectivity. These responses are not arbitrary. They follow pathways shaped by existing structure. Persistence is evident in Earth's long-term habitability. Despite asteroid impacts, volcanic winters, shifting continents, and changing solar output, the planet has maintained conditions compatible with life for billions of years, not continuously, not smoothly, but persistently. Self-modification is everywhere. Life alters atmosphere. Atmosphere alters climate. Climate alters erosion. Erosion alters crust. Crust alters ocean basins. The planet's current state is not imposed from outside. It emerges from internal interaction. Integration across parts is unavoidable. No Earth system operates in isolation. Atmosphere, ocean, land, ice, and life are entangled. Changes propagate across boundaries. Feedbacks cross domains. Memory exists in layers. Ice cores, sediments, isotopic ratios, fossil records. These are not memories in a conscious sense, but they are records that influence future behavior. Past conditions shape present responses. Threshold sensitivity is perhaps the most lifelike trait. Systems behave one way until they do not. Small changes accumulate. Then a shift occurs. The system reorganizes. This is characteristic of complex adaptive systems, including living ones. What Earth lacks is agency in the human sense. It does not choose. It does not anticipate. It does not act with purpose. But agency may not be a requirement for lifelike behavior. Many biological processes operate without awareness or choice. Cells do not decide to divide. Enzymes do not choose reactions. Purpose emerges from process rather than directing it. The discomfort arises when we conflate alive with conscious. Consciousness is a narrow and late-evolving phenomenon. Life existed for billions of years without it. Aliveness, if it means anything fundamental, cannot depend on awareness. This distinction matters because much of the resistance to calling Earth alive stems from fear of anthropomorphism, of projecting minds onto systems that do not have them. That fear is reasonable, but it may be misdirected. Recognizing lifelike properties does not require attributing thoughts or feelings. It requires acknowledging behavior. Another way to approach the problem is to consider whether alive is even the right word. Perhaps the difficulty arises because the word is overloaded. It carries biological, emotional, and philosophical meanings all at once. Some scientists prefer alternatives: active system, complex adaptive system, self-regulating network. These terms avoid emotional charge. They emphasize mechanism. They are precise, but they lack resonance. Alive resonates because it captures something intuitive. It gestures toward the sense that Earth is doing something rather than merely being something. That intuition has consequences. When people treat the planet as inert, actions feel external. When they sense responsiveness, actions feel relational. This difference influences behavior regardless of terminology. The danger is not in expanding the concept of life too far. It is in refusing to expand it at all when evidence suggests our categories are incomplete. Science has revised fundamental concepts before. Atoms were once thought indivisible. Time was once absolute. Space was once empty. Each revision was unsettling because it challenged basic intuitions. Each ultimately expanded understanding. Revising what alive might mean does not require abandoning biology. It requires recognizing that biology is a subset of a broader category of dynamic systems. Earth sits at an awkward intersection, too large to be an organism, too active to be an object, too integrated to be a machine, too slow to feel alive, too responsive to feel dead. Perhaps the most honest answer is that Earth occupies a category we do not yet have good language for. Alive is the closest familiar word, but it is imprecise. Not alive feels inaccurate. The tension remains. This tension mirrors earlier scientific unease. Gaia felt uncomfortable not because it was mystical, but because it forced confrontation with a system that behaved unlike either machines or organisms as traditionally defined. If Earth is alive in a way we do not understand, then understanding may require new concepts rather than better arguments within old ones. This does not mean abandoning rigor. It means extending it. One useful comparison comes from the study of emergent phenomena. Ant colonies display behaviours that no individual ant understands or intends. Traffic jams form without planners. Markets fluctuate without central control. These systems are not alive, but they exhibit organised behaviour. Earth is more than an emergent pattern. It integrates physical, chemical and biological processes across scales. It maintains conditions far from equilibrium. It persists through disruption. Whether that crosses the threshold into aliveness depends less on Earth and more on how we define the threshold. Perhaps aliveness is not a binary property. Perhaps it exists on a spectrum. Cells at one end, ecosystems somewhere further along, planetary systems occupying a different region altogether. Spectra make people uncomfortable because they resist clear categorization. But nature is not obligated to fit categories. Thinking this way does not trivialize life. It contextualizes it. It places individual organisms within larger patterns of organization. From this perspective, life on Earth is not separate from Earth's aliveness. It is an expression of it, a phase in how energy and matter organize under certain conditions. This idea can be misused. It can slide into vague spiritual claims or deterministic thinking. Guarding against that requires clarity. The planet does not care. It does not plan. It does not value outcomes, but it does behave, and behaviour is the foundation of scientific inquiry. The question then becomes practical rather than semantic. Does thinking of Earth as lifelike improve understanding? Does it help anticipate responses? Does it clarify risk? In many cases it does. Systems thinking reveals vulnerabilities missed by linear models. It highlights feedbacks. It emphasizes limits. Seeing Earth as responsive encourages caution, not because the planet might be offended, but because it will respond regardless of intent. The alternative, treating Earth as inert, encourages overconfidence. It suggests that problems are external and fixable without consequence. History suggests otherwise. Expanding what alive might mean does not force belief. It invites humility. It acknowledges that human categories are provisional. This humility is not weakness. It is alignment with evidence. Evidence that Earth is not passive. Evidence that it reorganizes. Evidence that it responds to cumulative change. As this understanding deepens, the question of aliveness becomes less about labels and more about relationship. How do we relate to a system that shapes us as much as we shape it? Language shapes relationship. Calling Earth a resource invites extraction. Calling it a system invites management. Calling it alive invites responsibility, even if the term remains contested. None of these framings are neutral. Each carries assumptions about agency, control, and consequence. Perhaps the most useful stance is to remain slightly uncomfortable, to resist settling the question too neatly, to allow alive to function as a provocation rather than a conclusion. If Earth is alive in a way we do not understand, then misunderstanding is part of the condition. Understanding may always lag behaviour. Signals may always be partial. Responses may always surprise. That is not a failure of knowledge. It is a feature of complex systems. For now, it is enough to sit with the ambiguity, to allow the word alive to loosen its grip on biology and stretch toward process, to notice that the planet beneath you is not simply there, but constantly becoming. Whether we ever find a better word may matter less than whether we learn to live with the implications of the one we have. Once the question of Earth's aliveness drifts beyond biology, attention almost inevitably turns inward, not toward the planet this time, but toward us, humans. Because if Earth behaves like a system that regulates, responds and reorganizes itself, then we are not standing outside that system observing it from a safe distance. We're inside it, embedded, participating whether we intend to or not. This realization can be unsettling because it destabilizes familiar roles. We're used to thinking of ourselves as actors and the planet as stage, as managers and the Earth as something managed. When that framing weakens, a different set of questions emerges. Are we components of a larger system? Are we disruptions within it? Are we temporary features like storms or ice ages? Or are we something else entirely? One of the most common metaphors that appears at this point is the idea of humans as cells within a planetary body. Cells consume energy, they reproduce, they alter their surroundings. Most of the time they contribute to the functioning of the larger organism. Sometimes they don't. The metaphor is appealing because it feels explanatory. It places humans inside the system rather than above it. It suggests scale. It implies limitation. But like all metaphors, it breaks down if taken too literally. Cells in a body do not reflect on their role. They do not build technologies. They do not intentionally alter the environment beyond immediate metabolic needs. Humans do all of these things. We are not passive units following biochemical rules alone. Culture, language, and technology give us leverage that far exceeds our biological size. Still, the metaphor is useful insofar as it highlights integration. A body cannot function without its cells, but it is not controlled by any single one. Health emerges from coordination, not dominance. When coordination fails, pathology appears. This leads to a more uncomfortable metaphor: humans as symptoms. Symptoms are not causes, they are expressions. They indicate that something within a system is changing or under stress. Fever does not cause illness, it reveals it. Pain does not create damage, it signals it. From this perspective, human behaviour could be interpreted not as an external attack on the planet, but as an internal expression of certain planetary conditions: abundant fossil energy, stable climate, rich ecosystems. These conditions allowed a species with particular cognitive traits to expand rapidly, develop complex societies, and amplify its influence. In that sense, humanity could be seen as what happens when a planet reaches a certain configuration. Not inevitable, but possible. A phase rather than an anomaly. This interpretation is unsettling because it removes moral clarity. It reframes human impact not as pure villainy or heroism, but as process. Something that arises under particular conditions and feeds back into those conditions. It also raises a difficult question. If humans are a symptom, what are we a symptom of? Energy availability is an obvious candidate. The rapid growth of human civilization coincides closely with access to dense energy sources, first through agriculture, then through fossil fuels. Fossil fuels are stored sunlight from deep time. Releasing that energy all at once enabled population growth, technological acceleration, and global connectivity. From a planetary perspective, this looks like a sudden surge in energy throughput. Systems respond to increased energy flow by reorganizing. Sometimes they become more complex, sometimes they become unstable, often both. In ecosystems, nutrient enrichment can lead to rapid growth followed by collapse. Algal blooms explode when excess nutrients enter a lake, then deplete oxygen and kill other life. The bloom is not malicious, it is responding to conditions. This analogy is uncomfortable but instructive. It suggests that human expansion may not be inherently unnatural, but it may be temporally mismatched to the system's capacity to absorb its effects. Another framing sees humans as a planetary disturbance, not a symptom, but a perturbation. In physics, disturbances introduce new energy or matter into a system, forcing it to adjust. The system may dampen the disturbance, amplify it, or shift into a new state. Viewed this way, humanity is not special because it exists, but because of the rate and scale at which it alters conditions: carbon emissions, land transformation, biodiversity loss, chemical pollution. These are rapid inputs compared to most natural processes. The speed matters. Earth's feedbacks evolve to handle gradual change. When change accelerates, those feedbacks may lag. The system overshoots. Stability weakens. This does not imply intent or blame. It implies mismatch. The system is responding to inputs faster than it has before. At this point, it becomes tempting to classify humans as a disease. The analogy appears frequently in popular discourse. Humanity as cancer, humanity as a virus, spreading uncontrollably, consuming resources, threatening the host. These metaphors are emotionally powerful but scientifically crude. Diseases and parasites are defined by their impact on a host's survival. Earth does not face existential risk from humans. The planet has endured far greater disruptions. What is at risk are particular configurations of life, including ours. Calling humanity a disease also collapses diversity. It treats all human activity as uniform. It ignores variation in impact, intention, and capacity for change. It frames the problem as existence rather than behaviour. From a systems perspective, that framing is not helpful. Systems do not remove components by moral judgment. They shift conditions until certain behaviours are no longer viable. If humans are incompatible with future planetary states, the system will not label us harmful. It will simply become less supportive of the conditions we rely on. This brings us to a different possibility. Humans as transitional agents. Throughout Earth's history, certain life forms have radically altered planetary conditions. Cyanobacteria oxygenated the atmosphere. Plants transformed land surfaces. Reef builders reshaped oceans. Each of these groups expanded rapidly, changed the system, and then stabilized or declined as new balances emerged. In this framing, humans are not an endpoint. They are part of a transition. Their technologies and behaviors are forcing rapid reorganization of planetary systems. What emerges afterward may include humans in altered forms, or it may not. This perspective removes both condemnation and comfort. It suggests that our significance lies not in permanence, but in impact. Humans are unique in one important respect, though: awareness. We are capable of recognizing patterns, anticipating consequences, and altering behavior intentionally. This does not grant control over the system, but it introduces a new kind of feedback. Conscious feedback. Most planetary feedbacks operate automatically. Ice reflects sunlight. Forests exchange gases. Oceans absorb heat. Humans can observe these processes and choose how to interact with them. This does not make us managers of Earth. It makes us participants with partial foresight. The question then becomes whether that foresight is sufficient to matter. Can conscious adjustment influence system trajectories meaningfully, or are we already committed to certain outcomes? System science suggests that timing matters. Interventions applied before thresholds are crossed can stabilize trajectories. Interventions applied afterward often struggle to reverse change. This makes the current moment feel precarious. Signals are emerging. Feedbacks are strengthening. Some thresholds may be near. Others may already have been crossed. Framing humans as cells or symptoms can be disempowering if it implies inevitability. But framing humans as entirely separate is equally misleading. A more accurate view may be that humans are a new type of component within the system, one that introduces feedbacks based on cognition, culture, and technology. These feedbacks can be destabilizing. They can also be stabilizing. For example, industrial agriculture often amplifies environmental stress. It simplifies ecosystems, depletes soils, and increases emissions. Regenerative practices, by contrast, strengthen soil carbon, improve water retention, and support biodiversity. Both are human activities. Their effects differ because they align differently with planetary feedbacks. The same is true for energy systems. Fossil fuels release carbon rapidly, overwhelming carbon sinks. Renewable energy alters energy flows without introducing new carbon. The system responds differently. This suggests that humans are not a monolithic force. We are a collection of behaviors, technologies, and choices interacting with Earth's dynamics. Some interactions amplify stress, others dampen it. In this sense, humans are not simply cells or symptoms. We are modifiers of feedback strength. That role is rare in Earth's history. Few species have altered planetary feedback so directly. Fewer still have done so knowingly. This awareness introduces ethical complexity, but ethics are not required for the system to respond. They are required only for us to decide how we participate. The temptation is to imagine a harmonious role. Humans as stewards, caretakers, guardians of balance. These narratives are comforting, but they risk overstating agency. Earth does not require guardians. It requires alignment. Alignment means designing systems that work with feedbacks rather than against them. It means slowing flows that destabilize and strengthening those that stabilize. It means accepting limits imposed by physics rather than negotiating with them. This does not require perfection. It requires direction. From this view, the question, "What are humans?" becomes less important than, "What do humans do to feedbacks?" Do our actions accelerate warming or dampen it? Do they simplify ecosystems or enrich them? Do they concentrate risk or distribute resilience? The answers vary by context. They change over time. They're influenced by power, culture, and knowledge. Seeing humans as part of Earth's system also reframes responsibility. Responsibility is not about guilt. It is about consequence. Actions have effects. Those effects propagate through feedbacks. Responsibility lies in understanding that chain and choosing accordingly. This perspective also dissolves some false binaries: humanity versus nature, technology versus ecology, progress versus preservation. These oppositions assume separation that does not exist. Technology is not outside nature. It is an expression of human behaviour, which is itself shaped by planetary conditions. The question is not whether technology is natural, but how it interacts with Earth's dynamics. Some technologies amplify extraction and speed, others enhance monitoring and efficiency, others support restoration. Their effects depend on integration, not intention alone. This is why simplistic narratives fail. Humans are neither purely destructive nor inherently benevolent. We are a force with directionality that can change. From a planetary standpoint, this makes us interesting rather than exceptional. The system is adjusting to a new internal driver that behaves differently from previous ones. Whether that adjustment results in coexistence or collapse depends on feedback timing, thresholds, and adaptation. Not on moral worth. This framing can feel cold. It removes comfort. It removes the idea that Earth cares what happens to us. But it also removes despair. The system is not out to eliminate us. It is responding to conditions we influence. In that space between indifference and agency lies possibility. If humans were merely a disease, there would be no point in reflection. If we were merely cells, there would be no capacity for choice. The fact that we can ask these questions suggests a different role. Perhaps humans are translators, entities capable of perceiving planetary signals and acting on them intentionally. Not perfectly, not collectively, but partially. Translation is imperfect by nature. Signals are misread, interests interfere, action lags. But translation introduces feedback loops that did not exist before, conscious ones. Whether those loops stabilize or destabilize depends on how they are used. This does not require believing Earth is alive. It requires accepting that Earth responds. The planet will not negotiate. It will not warn in language. It will not adjust its physics to accommodate preference. It will continue doing what it does. Within that reality, humans can choose how to behave, not as masters, not as villains, but as participants capable of learning. That learning may come too late, or it may redirect trajectories enough to matter. Systems are sensitive. Small changes applied early can have large effects. The uncertainty is unavoidable, but uncertainty does not equal helplessness. Humans do not occupy a simple role. We are not merely cells, not merely symptoms, not merely disturbances. We are something else entirely, a component of Earth's system that has become aware of its own influence and is now confronted with the consequences of that awareness. What we do with that position remains open. Listening is usually understood as a passive act. You stop talking, you pay attention, you wait for sound to arrive, someone else speaks, and meaning travels toward you through words, tone, rhythm. This model works well when the thing you are listening to shares your scale, your language, and your sense of time. Earth shares none of these. And yet, if there is any conclusion to draw from everything explored so far, it is that listening still matters. It simply has to be done differently. Listening to a living world does not mean expecting messages. It does not mean waiting for clarity or permission. It does not mean anthropomorphizing storms or interpreting earthquakes as intentions. It means adjusting how attention is applied. It means noticing response instead of voice, pattern instead of proclamation, consequence instead of command. For most of human history, listening to the world was a practical necessity. Weather patterns guided planting. Animal behaviour signalled seasonal change. The condition of soil and water shaped survival. This kind of listening was not philosophical. It was observational and immediate. People paid attention because they had to. As societies grew more complex and buffered themselves from environmental variability, that attentiveness shifted. Technology smoothed irregularities. Storage reduced dependence on timing. Global trade obscured local limits. The world became something to manage rather than something to listen to. Listening was replaced by forecasting, optimization, and control. These tools are powerful. They allow prediction and planning at scales that were once impossible, but they also create distance. When feedback is delayed or displaced, it becomes easier to miss. When consequences appear elsewhere or later, responsibility feels abstract. Listening differently begins with closing that distance, not by abandoning technology, but by using it to extend attention rather than suppress it. Scientific instruments are listening devices. Ice cores listen to past atmospheres. Satellites listen to changes in land, sea, and ice. Sensors listen to chemical shifts in air and water. These tools translate Earth's behavior into data streams that can be interpreted. But translation is only the first step. Interpretation matters. Data does not speak for itself. It requires context, comparison, and humility. It requires recognizing that signals may be subtle, delayed, or counterintuitive. Listening differently also means resisting the urge to reduce complex responses to simple narratives. Earth's reactions are rarely linear. A single change may produce multiple outcomes, some beneficial, some harmful, some both at once. For example, increased plant growth in response to higher carbon dioxide can look like resilience, but that same growth may be constrained by nutrients, altered by heat stress, or offset by drought. A signal that appears positive in isolation may be part of a larger destabilizing pattern. Listening requires holding multiple interpretations at once without rushing to resolution. It also requires patience with uncertainty. Earth systems are not fully predictable. Feedbacks interact. Thresholds are difficult to locate precisely. Waiting for absolute certainty before responding often means responding too late. Listening differently means acting on probability rather than proof, on direction rather than destination. There is a tendency to treat listening as an endpoint. You listen, you understand, and then you act. With Earth, listening and acting are intertwined. Action feeds back into the system. The response becomes new information. Listening continues. This iterative relationship resembles learning more than obedience. Another shift required is temporal. Human attention gravitates toward the immediate, the urgent, the visible. Earth operates on overlapping timescales. Some signals unfold over days, others over decades, others over millennia. Listening differently means expanding time horizons, not abandoning concern for the present, but situating it within longer arcs, asking not only what is happening now, but what has been changing slowly, consistently, and cumulatively. This shift in time perspective alters priorities. Short-term gains may conflict with long-term stability. Immediate comfort may undermine future resilience. Listening reveals these trade-offs without resolving them. Listening also involves recognizing silence, not the absence of sound, but the absence of expected response. When forests fail to regenerate, when species no longer return, when ice does not reform. These absences are signals. They indicate thresholds crossed. Silence is easy to misinterpret as stability. It often precedes rapid change. Learning to listen to silence requires memory, baselines, records. Without reference points, absence blends into normalcy. Each generation accepts diminished conditions as given, unaware of what has quietly disappeared. This is where listening becomes cultural rather than individual. Knowledge must be shared, memory preserved, stories told alongside data, not to romanticize the past, but to maintain awareness of trajectory. Listening differently also means confronting discomfort. Many planetary signals imply constraint, limits to growth, limits to extraction, limits to control. These implications conflict with dominant cultural narratives of expansion and mastery. It is tempting to reinterpret signals to fit preferred stories, to downplay risk, to emphasize uncertainty selectively. Listening requires resisting that temptation. This does not mean embracing pessimism. It means accepting that Earth's responses are not negotiable. Physics does not compromise. Chemistry does not debate. Biology adapts or disappears. Listening reveals this neutrality. It strips away the idea that good intentions alone alter outcomes. At the same time, listening also reveals opportunity. Feedbacks can be influenced. Trajectories can shift. Systems are sensitive, especially near thresholds. Small changes in direction can matter. This sensitivity is a source of both risk and possibility. Ignored, it amplifies harm. Engaged thoughtfully, it can amplify stabilization. Listening differently involves identifying which feedbacks are strengthening and which are weakening, which processes buffer change and which accelerate it, which interventions align with existing dynamics rather than fighting them. For example, restoring wetlands reduces flood risk by working with water flow rather than attempting to confine it. Rebuilding soil carbon enhances productivity while stabilizing climate feedbacks. These actions succeed not because they impose control, but because they listen to how the system already behaves. Listening also means acknowledging limits to knowledge. Earth systems are complex. Models improve, but surprises remain inevitable. Unexpected interactions emerge. Non-linear responses defy intuition. Listening differently accepts surprise as information rather than failure. It treats unexpected outcomes as signals of overlooked feedbacks rather than proof of unpredictability. This attitude contrasts sharply with a control mindset, which treats deviation as error. In complex systems, deviation is data. Another essential shift involves decentering human preference. Listening does not mean asking whether Earth approves of our actions. It means observing how Earth responds regardless of approval. Responses may be inconvenient. They may challenge economic structures, social norms, or political assumptions. Listening does not guarantee comfort. This is perhaps the most difficult aspect. Listening differently requires relinquishing the expectation that the world should conform to human plans. It replaces entitlement with attentiveness. That attentiveness does not require reverence. It requires realism. Realism recognizes that Earth does not exist to support any particular species indefinitely. Conditions that favor humans are contingent, not guaranteed. Listening reveals that contingency clearly. This realization can provoke anxiety. It can also provoke care, not because the planet needs saving, but because futures are shaped by present interactions. Listening to a living world also changes how responsibility is framed. Responsibility is not about guilt or purity. It is about participation. Being part of a system means actions have effects beyond intention. Listening clarifies which effects are likely and which are uncertain. It guides adjustment rather than absolution. This framing avoids both despair and denial. Despair assumes inevitability. Denial assumes irrelevance. Listening occupies the space between. It accepts that some changes are already in motion. It also accepts that not all outcomes are fixed. Another subtle shift involves redefining success. Success in a listening framework is not domination or optimization. It is coherence, alignment, functioning within limits. This may look less dramatic than technological conquest. It may involve slower growth, distributed resilience and redundancy. But these qualities are characteristic of systems that persist. Listening reveals that efficiency is not the same as resilience. Highly optimized systems often fail catastrophically when conditions change. Diverse, redundant systems adapt. Earth's history demonstrates this repeatedly. Monocultures collapse. Simplified ecosystems are fragile. Diversity buffers shock. Listening differently means designing human systems with this lesson in mind, not because diversity is virtuous, but because it works. Listening also involves scale awareness. Not every response needs to be global. Local systems matter. Regional differences matter. Earth's signals vary by place. Listening at appropriate scale avoids overgeneralization. It allows nuanced response. What stabilizes one region may destabilize another. This complexity resists simple slogans. It requires ongoing attention rather than one-time solutions. The idea of Earth as possibly alive often provokes either romanticism or rejection. Listening differently sidesteps that debate. It focuses on behaviour rather than labels. Whether or not Earth is alive in any meaningful sense, it behaves as a responsive system. Listening attends to that behaviour without insisting on classification. In this way, listening becomes an ethical stance without requiring moral language. It is about responsiveness rather than righteousness. It also reframes hope. Hope is not the belief that everything will turn out well. It is the belief that understanding can influence trajectory, that attention can matter. Listening supports that form of hope by grounding it in evidence rather than wish. There is also a quieter implication. Listening differently to Earth may change how we listen to each other. Recognizing complexity, delay, and feedback in planetary systems can foster patience in social systems. Both resist simple causation. Both require humility. This parallel should not be overstated, but it is suggestive. Systems thinking applies broadly. Listening improves when we accept that responses are shaped by context, history, and interaction rather than isolated intent. Returning to the original question, what if Earth is alive in a way we don't understand? Listening is the only reasonable response to that uncertainty. Not belief, not denial. Listening. Listening does not resolve the question. It makes it actionable. If Earth is alive, listening respects that without assuming communication. If Earth is not alive, listening still matters because the system responds regardless. Either way, the practice is the same. Listening differently also means resisting finality. There is no concluding insight that completes understanding. Earth's behaviour will continue to unfold. New data will emerge. Feedbacks will shift. Any sense of arrival would be premature. This is why listening must remain ongoing. It is not something done once, but something practiced continuously. In practical terms, this means building institutions that monitor, adapt, and revise. It means valuing long-term observation. It means protecting the ability to notice change. It also means acknowledging that listening does not guarantee consensus. Different interpretations will coexist. Interests will conflict. Decisions will involve trade-offs. Listening does not eliminate politics. It informs it. The danger lies not in disagreement, but in ignoring signals because they complicate narratives or threaten convenience. Listening differently accepts complexity without surrendering agency. As this exploration draws toward its end, there is no instruction to believe, no call to revere, no demand for certainty, only an invitation to pay attention in a way that matches the scale and nature of what is being observed. The ground beneath you is moving slowly. The air above you is circulating constantly. The oceans are carrying heat quietly. Life is altering chemistry continuously. Feedbacks are adjusting conditions relentlessly. These processes are not waiting for recognition. They proceed regardless. Listening differently does not mean expecting the world to respond to us. It means recognizing that it already is. Whether we choose to notice, interpret, and adapt remains an open question. For now, it is enough to sit with that awareness, to let the idea of a living world remain unresolved, not as a failure of explanation, but as an accurate reflection of complexity. Earth does not need to be alive to deserve attention. It only needs to respond, and it always has.